All right, now I want you to turn your cell phone off. All right, obviously we have a live program here today. We don't want those types of interruptions from the audience. Thanks for your cooperation with that. And welcome all to the Johns Hopkins Applied Physics Laboratory here in Laurel, Maryland for what promises to be a truly historic and great day for exploration. NASA's New Horizons spacecraft is just hours away from conducting the farthest exploration of worlds ever, a flight past the Kuiper Belt object known as Ultima Thule. Ultima, as we call it, is 1 billion miles beyond Pluto, the world that New Horizons famously revealed just 3 years ago. We have an exciting day ahead to mark this achievement, including opportunities to meet and hear from members of the New Horizons team from APL, Southwest Research Institute, and many of our partner organizations. We're glad you're here with us to bring in the new year, sharing in the exploration of an entirely new world. Our first speaker is Dr. Alan Stern, the principal investigator of the New Horizons mission from Southwest Research Institute in Boulder, Colorado. Alan was the driving force behind the mission to Pluto and the Kuiper Belt, and there's no better person to tell you the New Horizons story. Alan?
Thank you, Adrian. Thanks. Thank you. Well, welcome to APL and welcome to the Kuiper Belt on behalf of the entire New Horizons team. We are so excited to have you here and to be participating with us in this groundbreaking exploration. Now, what I'm going to do is give you a little bit of background on the mission. Our spacecraft is way out there, 4 billion miles from home, to get a close-up look, the first close-up look ever at a Kuiper Belt object. And I want to tell you a little bit about why we do this, and I'm not talking about the science. That's important. I'm not talking about the leadership of the United States. That's very important. I'm not talking about any of those other things. The basic reason we send the spacecraft out there is because these things are so far away that we don't have the technology to see them well unless we get up close. I'm going to start with this picture. This is one of my favorite pictures. I took it with a Hubble Space Telescope back in the 1990s. This is the best picture ever made of Pluto before New Horizons. Isn't it awesome? Can you see the polar cap? Yeah, the problem is to really understand a world like Pluto or Ultima or any other planet, you need an image more like this. With this kind of resolution, you can learn a lot. And to drive that point home, let me show you this planet, the Earth, pixelated to the same resolution as the best image we ever had of Pluto before we got up close. What could you learn about the Earth from this picture? Almost nothing. And I can drive that point home a little harder. Take a look. What are we looking at? Make a guess. Mars. Good guess. Completely wrong. You see, at that resolution, you don't know what you're looking at. So we send our spacecraft out there to be close, to use our cameras and spectrometers and other devices to understand these worlds. In this case, we sent New Horizons, and this is the spacecraft. It was built right here at APL back in the early 2000s. This picture was taken down in Florida in a clean room at the Cape about a month before launch. And here you can see, because the people are next to it, how small the spacecraft is. It only weighs about 1,000 pounds with fuel. But inside of that spacecraft is everything we need for the entire journey to cross the solar system and explore these brand new places. We have guidance systems, main computers, we have data storage, power generation, thermal control, and more. And we communicate back to Earth through that dish antenna that you see at the top. We're powered by a radioisotope thermoelectric nuclear powered generator. It's that black hair curler looking device on the side. And 7 scientific instruments on board the spacecraft. As I said, cameras and spectrometers and in situ instruments as well. This is a very advanced spacecraft. In fact, the instruments on board have literally orders of magnitude more capability than any first reconnaissance mission sent to any of the other planets. 7 scientific instruments some of them have sort of funny names: Lori, Ralph and Alice, Rex, SDC, SWAP, and Pepsi. And let me tell you about each one very briefly. You'll hear more later. Lori, built here at APL, is a telescope about a 20-centimeter telescope that feeds a CCD camera, and it's our highest magnification imager. The best images that you'll see of Ultima will come from LORRI. Ralph is a more all-singing, all-dancing color camera and infrared mapping spectrometer that allows us to actually take the fingerprint of what the surfaces, like Ultima's surface, are made of. And then Alice is an atmospheric spectrometer called an ultraviolet spectrometer built at the Southwest Research Institute in San Antonio, where I work. Rex is a part of our radio communication system, and it's our radio experiment. And Rex is going to be taking the temperature of Ultima Thule. We're going to try to bounce radar waves off of it from the Earth and measure its radar reflectivity. And at Pluto, it measured the temperature and pressure profile of the atmosphere. SDC is a student-built instrument that measures dust impacts on the spacecraft so we can trace the density of interplanetary dust across the solar system. SWAP is a solar wind monitor that we used at Pluto to determine Pluto's atmospheric escape rate. And Pepsi, also built here at APL, is a high-energy charged particle spectrometer. And both SWAP and Pepsi will be looking for the interaction of Ultima Thule with the solar wind, the heliosphere, and the charged particle environment out there. So we built this spacecraft in the early 2000s, and we launched it from Florida in January of 2006. And it took about 40 minutes for the rocket to give us all the speed that it took to get all the way out to Jupiter, our first stop on this long journey. And Jupiter was our test flyby and also a gravity assist for us. It's 500 million miles from the Earth, but barely over 10% of the way to where we are now. Imagine that. We spent the next 8 years after flying by Jupiter crossing the entirety of our solar system. An 8-year journey that lasted from 2007 to 2015 and covered 3 billion miles. New Horizons travels at a speed of almost 10 miles per second. Think about that. 30 seconds, and you can come from New York all the way down here to DC if you were riding on New Horizons. And we're doing that speed 24/7, 52 weeks a year after year to cross our solar system. It is vast. And now we've arrived at this wondrous place called the Kuiper Belt, this third zone of our solar system. Beyond the terrestrial planets lie the giant planets, and beyond the giant planets lies the Kuiper Belt. We intercepted Pluto's orbit just as Pluto was crossing our trajectory, the red line here, in the summer of 2015. And what a spectacular place Pluto turned out to be. And it taught us so much about not just itself, but about dwarf planets in general. It taught us that small planets can be as interesting and as complex as large planets like the Earth and Mars. And it even rewrote the textbooks in teaching us that small worlds can be active billions of years after their formation. Let me take you on a ride across the surface of Pluto with images made by the LORRI camera on New Horizons. We're going to start up near the North Pole, and we're going to come right down that track. And here we go. Now, realize this world is so far from the sun that the temperatures out there are close to absolute zero. Everything you're seeing here is made of ice. Those are craters, and you can see their windows into the interior of Pluto. We're going to come up on some badlands in a minute, and then some mountain ranges. And these mountains are huge. You can see the scale bar there, 6 miles. And they stretch, in some cases, 15,000 feet into the sky. And then, after the mountains, we're off onto this vast nitrogen glacier, Pluto's heart, called Sputnik. And you can see dune fields there and other complexities that I won't have time to get into, but what an amazing place. And now we've left Pluto, and we're on our extended mission. We're going farther out to explore the Kuiper Belt. And tonight, New Horizons will make the first exploration ever of an object in the Kuiper Belt, Ultima Thule. As we ring in the new year, New Horizons will be making its closest approach, and we appreciate you coming to join us. So what is this extended mission all about? It really has 3 aspects to it. First, we're using that LORRI camera that I've told you about, which has a telescope, to actually look at Kuiper Belt objects that we pass in the distance, to study them, to put Ultima Thule in context. We're studying their rotation rates, the number of satellites they have, their shapes, and other details with that LORRI camera. Secondly, we're using the SWAP and Pepsi instruments along with the Alice ultraviolet spectrometer and the dust counter to study the environment out there. What's the radiation environment like? How much dust is there in the Kuiper Belt? Things like that. We even look at the gas that's out there that comes from the solar wind. But the centerpiece of this mission is what we're doing today. It's the close flyby of Ultima Thule. And when we first started to go after Ultima Thule, we thought it might be a binary object. This is a very dramatic view. We're not actually coming this close. We have new information that indicates it's probably not a binary. It's more like a monolithic object. But we hardly know anything about it. Even after the 3.5 years that we've been chasing it down and studying it with the Hubble Space Telescope, we've only been able to learn a few things about it. We know that it's about 30 kilometers in size. We know that it's reddish. We know its orbit very precisely. And we don't know much else. It has an irregular shape. That's really everything we know. That's all going to change. It's going to change this week because New Horizons is bringing these amazing sensors to bear. And as a result, we're going to map Ultima's surface in great detail. We're going to map its surface composition. We're going to determine if it has an atmosphere. And we're going to look for satellites and rings that might be orbiting it. So fasten your seatbelts for exploration. New Horizons is coming, and it's not going to be very long. Barely 10 hours from now, closest approach. Thank you very much.
Thank you, Alan. As you've heard, New Horizons is speeding through a distant region of space known as the Kuiper Belt, a mysterious expanse of icy, rocky worlds thought to be the building blocks of the planets. To take us inside this third zone of our solar system is Dr. Hal Weaver, the New Horizons project scientist from the Johns Hopkins Applied Physics Laboratory.
Thank you, Adrian. So let's give you a little bit of background on the Kuiper Belt. First, let's start with his namesake, Gerard P. Kuiper, who's a Dutch-born American astronomer who's often called the father of planetary science because of the pioneering work he did in establishing the entire field. Now, around 1950, he actually decided to tackle a really difficult problem. How did our solar system form? And when he looked into the details of that, he realized that the solar system shouldn't end at Neptune and Pluto, which was thought to be the edge of our solar system at that time, but there should be lots of objects beyond Neptune and Pluto. Now, he didn't get all the details right about that, but the basic idea that there's a swarm of objects beyond Neptune is correct, as we now know since the early 1990s, when we've now discovered almost 3,000, around 3,000 objects in the Kuiper Belt. And a very simple way of discussing the Kuiper Belt is to call it a vast swarm of bodies in a sort of a donut-shaped, torus-shaped ring surrounding the sun just beyond Pluto. And here's an artist's drawing of the architecture of the solar system. And the Kuiper Belt is represented by all of those sort of reddish dots. And look at the vast expanse of the Kuiper Belt. The cyan circles are the orbits of all the planets. Pluto's orbit is in white there. And we like to refer to the Kuiper Belt as the solar system's third zone. In order to see the first zone, you have to actually zoom in to near the sun, what we call the terrestrial planet region, relatively small rocky planets, Mercury, Venus, Earth, and Mars. And then you step beyond the asteroid belt, which you see there, into the realm of the giant planets, and that's the second zone. Jupiter, Saturn, Uranus, and Neptune, they have cores that are formed of 10 times the mass of the Earth in the cores of these objects, and then giant envelopes of hydrogen and helium gas. And then and now we know about, not since the 1990s, we finally know about the third zone, and it's actually the most populated region. But along the way, in 2005, some of you may have remembered that an object called Eris was discovered and caused us a lot of problems because at the time it was thought to be a little bit larger than Pluto. And so that motivated a discussion, a pretty contentious discussion at times, about what is a planet. And we don't have time to go into all the details about that right now, but I think all of us are in agreement. There's a consensus now that there's this new category of objects in the solar system that we call the dwarf planets. And these are very interesting in their own right. As Alan just showed you, Pluto is an amazing place. And Eris is also a dwarf planet, and there's a handful of others out there in the Kuiper Belt. But now let's talk about the path, the trajectory of the New Horizons spacecraft is that yellow curve as it's heading out. We've now said goodbye to Pluto 3.5 years ago, and Pluto is like the gatekeeper to the Kuiper Belt. It's on the inner edge, and Ultima Thule is in the thick of it, the densest portion of the Kuiper Belt. And this is exploration at the frontier of planetary science. And the neat thing is that the formation of the solar system, this architecture, is not unique to our solar system. We now know this is something that's just been discovered in the past 20 years. There's it's a very common process that produces planetary systems around stars. And in fact, we think most stars in the galaxy and indeed in the universe have planetary systems around them. And the way that this works is if you start in the middle here in the far left, you have a giant cloud of gas and dust slightly rotating that has a condensation in the center that becomes a star. And as that star forms and it rotates, the whole gas cloud rotates, it then collapses into a disk, which is in the center there, and you start to get condensations in that disk that become planets, and the planets gobble up all the material along their orbits, creating gaps, and then finally all of that gas and the residual gas and dust get blown out of the system, producing a mature area that you have to the far right. And we actually, one of the nice things about astronomy is that you can actually look at examples of these from completely different eras, like early, the figures down in the lower left and in the middle at the bottom. These are early planetary systems, basically. Our sun is about 4.6 billion years old. We're talking about 20 to 30 million years old. You have examples in front of our eyes produced by telescopes of, in the middle here, Beta Pictoris disk, very much like a Kuiper Belt disk. And so one of the things that we're excited about in doing a mission like New Horizons is this not only telling us information about our own solar system, but it's giving us information that's going to help us to understand planetary system formation in general throughout the universe. Thank you very much.
Thank you, Hal. We've never explored a small Kuiper Belt object, and even from this close, Ultima Thule is still a little more than a bright dot to New Horizons. But we do have some early reconnaissance on our flyby target, and to tell you about that is Dr. Kathy Olken, a New Horizons Deputy Project Scientist from Southwest Research Institute.
Thank you, Adrian. Good afternoon, everyone. I'm excited to be here and tell you what we know about Ultima, specifically because this is all going to be obsolete within the next few days. It's going to be overcome by all the new data. So as you heard from Hal, that Ultima Thule lives in the Kuiper Belt. We believe it formed and lived its whole existence, 4.6 billion years of solar system evolution in the same orbit where it is now. You can see this graphic. The planets are the red, yellow, cyan, and other dots there. And the line is the New Horizons trajectory. And you can see all the other sorry, it's a movie, trying to get it to go. So I will tell you. So all the other points are Kuiper Belt objects, and they actually show the orbits of real objects. So this isn't an artist's rendition of what the Kuiper Belt looks like. It's actually the different populations. And the red dots that you can see there are the objects that are like Ultima. They orbit in the same plane as the planets in the solar system, and they have a circular orbit. And so that means that they have been there the whole time. They haven't been perturbed by other large bodies like Uranus or Neptune. So that's why we say that it is primordial. And so this is a remnant from solar system formation. So how do we know that it orbits in the same plane and has a circular orbit? Well, it was discovered, Ultima was discovered by the Hubble Space Telescope. We had a program searching for objects that we could fly by after Pluto, a dedicated search to look for and find objects we could fly past. And this is one of the objects found in that search. It was found only in 2014. And you can see this is the discovery image. It's a stack of 5 different images. And so you can see Ultima as it moves past stars in the background. Now, New Horizons also provides information about where Ultima is. We've been taking optical navigation data on approach, and this is a loop of Ultima relative to the very dense star field behind it. And you can see it's the object that starts near the middle, and then it's creeping up, and it's getting brighter. And that is Ultima. And we know that it's in the Kuiper Belt because you can see it move relative to the fixed stars. On the right, you see subtracting all the stars out so that you can just see Ultima. And up until recently, this has been our best view of Ultima, much like the image that Alan showed of the HST image, and now we have these New Horizons images. But there's not a lot of detail there. But we're going to change all of that with the observations we're taking right now on the spacecraft, and we'll be continuing to take throughout the evening. The other way we know about Ultima is from a stellar occultation, and that's from watching Ultima pass in front of some of those stars in the field. And you can see the animation here, the star disappears. That's because Ultima passes in front, and there's not enough reflected light to see Ultima from the small telescopes that we were observing this event from. You can see the small telescope there. This was in Senegal in Africa. We had to travel to be in the right place at the right time, just like you need to do for an eclipse observation. Now, so from the occultation, we have an idea of how large Ultima is. And it's about 15 to 20 miles across. We do not believe it's round, like in this image, but it gives you an idea of how it fits relative to our surroundings here. So it would fit nicely in between Baltimore and Washington, D.C. But it's nowhere near here. We also know that there's no large distant satellites in orbit around Ultima. And we didn't know that until recently. With the New Horizons data, we've been understanding more and more and been able to place constraints on what might be in the vicinity of Ultima. And so we know that 85 miles beyond Ultima, there's no satellites greater than 6 miles. And we've really been able to get better and better constraints as time goes on. But with these observations that we've had so far, there come other questions. Is it a binary? Is it a contact binary? Is it potato-shaped? As you heard from Alan earlier, we probably don't think it's a binary object anymore. But we're going to learn more about that in just the days to come. The one final piece of information that we know something about on Ultima is its color. We have color information from the Hubble Space Telescope, but it just tells us that it looks reddish. We don't have a lot of detail. And the color is important because it tells us what the surface is made of. We don't know a lot of detail yet, but we're going to be getting data soon that reveal a lot more about the color and how the color might change across the surface. So you're going to find out more just in the next week. Thank you.
Thank you, Kathy. When New Horizons zips past Ultima Thule at more than 30,000 miles per hour, what is it looking for? John Spencer, a New Horizons deputy project scientist from Southwest Research Institute, has played a critical role mapping out the plans for this historic exploration of Ultima, and he's here to describe the flyby plan.
Thank you. Yeah, so I'm going to tell you just a little bit about what we're doing right now, what we've been planning all this time, and what is now finally happening, which I'm having trouble believing that we're really doing this stuff now. So here's the basic facts about the flyby. We're flying by this evening or tonight, just after midnight local time, 22,000 miles, much closer than we flew past Pluto, because it's a smaller object, so we want to get closer to get a good look. We're flying by at 32,000 miles an hour. This is a speed that's going to, we're going so fast we're escaping the sun's gravity, and we're just going to continue out into the universe at that speed. And this flyby is 44 times the distance between the Earth and the sun. That's how far out the spacecraft and Ultima are. And this is a record-breaking distance for any planetary encounter. And we're a billion miles beyond Pluto. And this is not an easy thing we're doing here. The target is tiny compared to Pluto. It's 80 times smaller. That means much more accurate targeting. And we're flying by much closer, which also means more accurate targeting. So pointing the cameras in the right direction is a real challenge. Just to make it harder, we're not actually sure where it is. We can see very accurately from the images you've seen where it is as we approach, but that tells you where it is in the sky. It doesn't tell you exactly how far away it is. So the images we take will be scanning a wide region around Ultima so that we're sure to catch the region where it actually is in that range of uncertainty. We don't know anything about these worlds up close. We don't know the environment. We've been concerned about we might run into dust or debris, something that might harm the spacecraft. And so we've done a lot of work to make sure this doesn't happen, and we're now very confident that we're flying by a safe environment that we can explore with safety, but it took us a lot of work to get us to that point. The light level out there at Ultima is probably similar to what it is in this room outside of these bright lights. It's really dim out there, and we have a dark target, so we need long exposures. We have to hold our camera really steady to get those pictures. We don't have as much power as we had at Pluto because our radioactive power supply is gradually decaying, so we have to be very careful which instruments we switch on at which times so we don't overload the power system. And then it takes 12 hours for a signal to get to the spacecraft and for a response to come back to the Earth. So we're not doing anything real time. It's all pre-programmed. The spacecraft is doing its thing now, and it will be sending us back the information on how well it is doing. But we have no ability to control it in real time. Here's a sketch of the flyby itself. This is covering a time of about a couple of hours around the closest approach. So this is what will be happening late tonight and early into the small hours of tomorrow morning after New Year's. We're doing a very carefully coordinated series of observations with all our instruments to learn the most we possibly can about Ultima during this flyby. And so the colors here tell you which instruments are operating at different times. We're doing infrared scans, then we're actually measuring the surface temperature. We're using a radio antenna to pick up the microwave radiation from the surface. We're taking color, we're taking more infrared data to map the surface composition, then our best color, and then our best black and white images near closest approach. Then we look back, we turn back, and we watch the receding crescent backlit by the sun as we head out from Ultima. At that point, we'll also be looking at the night side temperature, something you can never do from the Earth because you can't see the night side of these objects looking out from the sun. And more crescent images. And then we're going to be looking back towards the sun, and we'll be looking for any gas that might be in the surroundings, maybe gas that's coming off from Ultima. Not that we expect to see this, but we're going to do everything we can to investigate it. So we'll be looking for any gas that might be absorbing the sunlight as we look back to the sun. And so it's a very comprehensive investigation that we're going to be doing, and we're very excited to be doing it finally after so much planning. Here's an animation of the closest approach sequence. We're 100 times further away than Ultima than its diameter, so it makes it look a little bit closer here. You'll see the spacecraft rocking backwards and forwards as it scans across Ultima and takes these observations of the surface in all these different instruments that we have and covers the area, not just of Ultima itself, but the areas on either side where it might be, because we're not going to know exactly where it is. And okay, one more slide. So we have a really comprehensive exploration here with all our instruments, and the best images that we expect, that we are sure that we will get, have about 400 foot pixels. That means we'll get 200, 250 pixels across the object. But we also, with our narrow-angle lorry camera, we're trying for much higher resolution images than that. We're not sure if that will succeed because it's hard to point it in the right direction with that very narrow field of view, but the data we've been getting recently has been looking really good, so we have more confidence of doing that, but it's still no guarantee that we'll get those highest resolution pictures. So we're really rooting for the spacecraft to deliver on those. Then we get color images with a little bit lower resolution than the best black and white images. We'll be measuring the composition of patches about as small as a square mile on the surface. We'll get hundreds of such measurements across the surface to look for variations in the composition across the surface with our infrared instrument. And as I mentioned, we're looking at the daytime temperature and the nighttime temperature. By comparing those, we'll get some information about what the surface is made of, how well it can retain heat. We're doing something very ambitious, which is 6 hours before closest approach, we're sending a blast of radiation up from the Deep Space Network towards the spacecraft. When that reaches the Ultima system, it's going to be bouncing off the surface, and we'll try and catch that reflected signal from the spacecraft's main antenna. We don't know if that'll work, but we're giving it a shot, that we'll be able to get that reflection and learn more about the surface in another unique way that way. And then, as I mentioned, we'll be searching for an atmosphere, both with our ultraviolet instrument and with direct images to see if there is any gas or dust coming off from this object, just in case, because we might be surprised and see something strange like that. And we're looking for rings and moons as well. And I think that is my last slide. It is, okay. Thank you, that's all.
Thank you, John. As New Horizons approaches Ultima Thule, we have a series of simulations from NASA's Eyes on the Solar System. This first video shows approaches and observations by the ALICE instrument.
Welcome to New Horizons Now. I'm Christy Marin from New Horizons Communications at the Johns Hopkins University Applied Physics Lab here in Laurel, Maryland.
And I'm John Spencer. I'm the New Horizons Extended Mission Science Planning Lead and Deputy Project Scientist from Southwest Research Institute in Boulder, Colorado.
Thanks, John. New Horizons is currently heading toward the first ever flyby of a Kuiper Belt object. Our flyby target, Kuiper Belt Object 2014 MU69, nicknamed Ultima Thule, is an ancient KBO and a building block of the planets. John, can you tell us what is happening right now on board New Horizons as it approaches Ultima Thule?
Yes, this is an exciting milestone right now because for the first time we're using our full suite of remote sensing instruments. Right now we're looking with the ALICE ultraviolet instrument at Ultima Thule to look for any hint of gases that might be coming out of this object if it was active. So it's the first time we're close enough that we can use that instrument and maybe get some signal. We're also starting to observe with our infrared instrument that will start to map the surface compositions. So things are really happening now.
Great, thanks, John. And this is New Horizons Now.
All right, thank you. What we're going to do now, and welcome back, we're going to set up for a press conference. So what we're going to do is we're going to have a short break, and then at about 2 o'clock, I believe the press conference is going to begin back in here. That's open to everyone. That's going to run from 2 to 3, and then we'll resume our program at about 3:15. Thank you, everyone.
on the cusp of a new year, we're about to make discoveries of an entirely new world. Good afternoon. We're live from the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. I'm Mike Buckley from the APL Communications and Public Affairs Office. And NASA's New Horizons spacecraft, in just about 10 hours, will zoom past a Kuiper Belt object nicknamed Ultima Thule, the farthest exploration of worlds in history. So we're here today to update you on the status of the spacecraft and to lay out the science plan for this flyby, which is going to occur 4 billion miles from Earth. We have the panel here. We're going to take questions from the media assembled here at APL, and we're also going to take some questions over the phone. In fact, I'm going to get right into the panel and introduce them, who are going to bring us up to speed on the mission. First, we have Alan Stern, Principal Investigator, Southwest Research Institute in Boulder, Colorado. Helene Winters, New Horizons Project Manager from the Johns Hopkins Applied Physics Laboratory. Fred Pelletier, the Navigation Team Lead from Kinetics Incorporated. And John Spencer, New Horizons Deputy Project Scientist from Southwest Research Institute. Dr. Stern.
Good afternoon. This evening, the United States, through NASA and the New Horizons Project, will make history. The farthest exploration of worlds ever attempted, 4 billion miles from home. I'm here to tell you that the spacecraft is on course, it's healthy, it's conducting observations as we speak, and it's going to arrive on time at 33 minutes past midnight, 33 minutes into the new year, Eastern Time. New Horizons launched in 2006 on a journey to the Kuiper Belt, the third zone of our solar system. Traveling at a speed of over about 10 miles per second, 24/7, 52 weeks a year, it has crossed this 4 billion mile ocean of space to the very frontier of our solar system. You see here in this image behind me the trajectory of our flight out into that disk of material we call the Kuiper Belt. The Kuiper Belt is a scientific wonderland that can teach us about the origin of our solar system and the planets in it. The first objective of the New Horizons mission was to explore Pluto and its system of moons, and we did that spectacularly in the summer of 2015. And after revolutionizing our knowledge, not just about Pluto and its moons, but also about dwarf planets in general, we went on, now on an extended mission, where we're going out into the Kuiper Belt almost twice as far as Pluto, ultimately. We've traveled another billion miles in that time since the summer of 2015 to intercept this small body we call Ultima Thule, this Kuiper Belt object. And it is history-making, what we're doing. As we've said a couple of times, this is the most distant object ever explored. But it is, in addition, because of the cold temperatures out there, the most primitive object ever explored, and therefore probably the best time capsule we've ever had for understanding the birth of our solar system and the planets in it. Because the target is very small, the flyby is going to be very brief. The lead up to Pluto was more than 10 weeks long. We were only able to resolve Ultima for the first time from about 1 million miles away yesterday in an image that John Spencer will be showing you. This is also a much more challenging flyby than the flyby of Pluto, and it's taking place at an auspicious time on New Year's Eve and New Year's Day 2019. The reasons that this flyby is tougher are many. We're farther from the Earth, and so the communications times are much longer. We're farther from the sun, and so the lighting levels are lower, making it more difficult for our cameras and spectrometers to operate. In addition to that, we don't really know the environment around Ultima as well as we did know the environment around Pluto, and so we're taking some risks. Also, its orbit is not perfectly known, and making the intercept is tough. And finally, because the spacecraft is older, its power generator that's on board produces less wattage, so we have to manage our power much more carefully. All of these things add up to a much tougher, much more challenging flyby than what we had to do at Pluto, and I can't promise you success. We are straining at the capabilities of this spacecraft, and by tomorrow we'll know how we did, so stay tuned. There are no second chances for New Horizons. And I want to just close by saying, you know, the reason that New Horizons has been successful in its flight so far is because of the New Horizons team, an amazingly talented team of men and women, engineers, scientists, technicians, flight controllers, each of whom has been dedicated to this project and really poured their careers and their life, for that matter, into it. And there are many stories of individual contributions that made this project possible. There are many teams. We are a team of teams. But I want to point out one particular challenge and one particular person today, because we would not be here if it were not for him. You know, New Horizons is the first spacecraft to launch on a mission when it didn't have a target. We only discovered Ultima Thule in 2014 using the Hubble Space Telescope. And the man who's responsible for that discovery is our co-investigator, Dr. Mark Bowie of the Southwest Research Institute. And not only did Mark discover Ultima, he also made it possible for us to intercept it by developing state-of-the-art techniques to perfect our knowledge of its orbit well enough to hunt it down in the darkness of the Kuiper Belt from a distance of 1 billion miles away. Give him another round of applause. That's why you're here. Thank you, Mark. Okay, and with that, I'm going to turn it over to our project manager, Helene Winters.
Thank you, Alan. Okay, I'll update you on our flyby plans. Okay, our payload is comprised of 7 science instruments. 3 of them are cameras, and we have the REX instrument, which uses our own RF antenna. And we also have 3 instruments to better learn about the particles. So the LORRI camera is the first device, the first instrument that we were able to use to see Ultima Thule. It's our long distance and ranging camera. We were first able to see Ultima Thule with it on August 16th of this year. And since then, we've been taking images, and it's gotten closer and closer, and we've been able to image it better and better. Initially, we had to use long exposure times and do what we call co-adding, take multiple pictures and layer them over each other so to see it in the sky. At this point, we don't need to do that. We don't need to co-add to see it. We can see it with the LORRI camera by itself. If you look at this crowded star field, it would be very hard to detect Ultima Thule in it. And Mark Bowie had used a technique similar to what Clyde Tombaugh had used to find Ultima, taking pictures, multiple pictures over a period of time and seeing it move in the night sky. Now here is where it actually is, where Ultima Thule actually is in this sky, in the region of Sagittarius. At the top part of the oval that you see, the ellipse that you see, you'll see it appear when I show you this film clip. This is layered multiple images taken over the last month. And you can see it growing out of the center. So those are the pictures we've taken, like I said, over the last month with the LORRI camera. And now we're able to see it just now with the Ralph camera as well. So here's our timeline of flyby activities. We have, you can see in August where we first were able to image Ultima Thule with LORRI. We've been taking what we call optical navigation images, or OpNavs, with LORRI since then. And still, we're taking them OpNavs daily. We were taking them at that point to better understand its position. And then we did a series of maneuvers, trajectory correction maneuvers, to adjust our spacecraft's trajectory to more precisely target that close flyby at 3,500 kilometers or 2,200 miles from the center of Ultima Thule. As we got a little closer in the November time frame, we also made hazard observations. We took more pictures to look very closely for any potential hazards, perhaps moons or rings that might obstruct our path along the trajectory. We did not detect any, so we were able to fly our optimal trajectory, 3,500 kilometers. Had we found any obstructions, we could have flown by at 10,000 kilometers. We would have had a divert maneuver to fly to that farther distance. But we were able to fly by at the optimal distance for the science folks. And you can see at the vertical line is where we have our closest approach. And then we're downloading data already, downlinking data from the spacecraft. And we'll continue to downlink data. We'll get just a bit before we go into solar conjunction from the 4th through the 9th of January, where the Earth will be on the far side of the sun from the spacecraft. So that would interrupt our communications with the spacecraft. So during that time, we won't be able to get much data down. And then we'll resume our downlink beyond that. And it'll continue for a period of about 20 months. Okay, here we have an expansion of the inner part of that timeline. We recently were able to make timing updates based on those op-navs as Ultima Thule gets closer and closer. We were able to tweak the information that we store on board the spacecraft about the location of our target body. So we were able to adjust the timing by 2 seconds to better image it, and adjust our pointing so our images more accurately capture as centered as we can be on Ultima Thule. And then you can see closest approach at the circled green diamond. So the blue diamonds before closest approach on the timeline are what we call our fail-safe images, where we've taken images on the approach in case anything should happen at flyby to the spacecraft where we wouldn't be able to get the data down. So we have those on the ground, and we'll be showing those. Basically, the fail-safe image will show, the second fail-safe image will show at our press conference tomorrow, and on the 1st at 11:30, and then each day for the next couple days, then we'll have press conferences at 2 to show the images that we've collected from the day before. And then beyond closest approach, you see where we have our essentially our quick look images, our first opportunity to look at the flyby images. They won't be at full resolution that we'll see, but John will talk to you more about that, the images that we'll see later as we get closer and are able to downlink those.
Okay, thanks. Navigation is about driving the bus to the destination within the requirement set forth by the scientist. You see on this image a close-up view or our flyby trajectory at closest approach, where we're going to fly due north of Ultima Thule, about 2,200 miles away. And the goal of the navigation team is to determine the relative positioning between the spacecraft and its target. And we want to put this within roughly a 40 square miles box and get the timing within 80 seconds or so. So considering that we are 1 billion miles beyond Pluto, this is quite an achievement and a challenge for us. And as my colleagues mentioned, we are using the LORRI imager to get our relative positioning. But the first thing we need to really capture or understand is the position of our spacecraft in the solar system. So we achieve this by using the Deep Space Network, which is a series of antennae that NASA has that are strategically positioned around the globe in California, Spain, and Australia, that are designed to basically see the NASA spacecraft all the time. And then we are basically using these antennas not only for uplinking comments to the spacecraft or downlinking images, but also to get our velocity and ranging information for the spacecraft. Then we need to worry about our targets. So as it was mentioned before, and thanks to Mark Bowie's work, we have used the Hubble imagery to get an initial look of where Ultima's orbit were. Now, the missing information with this was the depth of Ultima Thule as seen from the Sun or Earth. And that's only when we combine the LORRI imagery on board that we acquired starting in August up until very recently with the Hubble imagery that we can really get the positioning of Ultima. So as we do this over the time, we need to allow ourselves to adjust our trajectory. So what we do is we design course correction maneuvers, and we performed the last one on December 18th. And the missing piece, the final piece, was to acquire the images up to the 30th of December to basically get us the final relative positioning so we could uplink that, the final pointing update to the onboard the spacecraft. And we did that. We designed this solution 2 nights ago. I wanted to go back to the optical imagery that we did, that Elaine presented, and maybe give a little more detail on the challenges. It's what you see on the left is the raw imagery that we are working with, and there's a lot of stars in there. The resolution is not the best, so it's a real challenge to really pick out where Ultima is. So what we do is we do a series of processing. One piece is co-adding, like Elaine mentioned, and we also are refining the resolution on the imagery, since we have many images to work with. And lastly, we are subtracting the stars to clean it up, and that's the image you see, or the video you see on the right. So I want to end up with a global view of our trajectory work since launch, maybe focusing after the Pluto flyby in 2015. We did a series of 6 course correction maneuvers. The first one was 100 days after Pluto, where the maneuver was fairly large, and we had to break it up into 4 pieces to make sure that the spacecraft could execute it. And then the last one, like I said, was on December 14. And I compared this to essentially trying to hit a requirement size of the size of a golf ball if you were to start from the West Coast and try to hit your bullseye on the East Coast. So with that, I think everybody's excited to try to see some science imagery. I'll turn it over to John.
Thank you, Fred. Yes, so I'm going to tell you a little bit about what we hope to accomplish with this flyby. We have a series of science objectives. One of the prime ones is to map the geology of Ultima, whatever craters it might have on its surface, whatever fractures, other topography, anything that will give us clues as to how its surface was formed. We want to map the composition and color of the surface. The color itself gives us information on the composition. So we're looking for ices on the surface, other things that we probably haven't imagined yet. A particular mystery is we want to know why Ultima and objects like it in the Kuiper Belt, there are hundreds of thousands of objects we think like Ultima out there, tend to be dark and red. We think they're mostly made of ice, but their surfaces don't look icy, they look dark and red. So we're hoping to delve into that mystery. We're also looking for satellites and rings, and we can search for moons that are very small, less than a couple of 100 feet across. We haven't found any moons yet, and this image shows a view from a couple of weeks ago where we were looking in the area around Ultima to see if there was anything hazardous. And we didn't see any hazards, we didn't see any moons, any rings, but we can look with much more sensitivity now because we're so much closer, and who knows what we might find. And after we fly past, we'll be looking back towards the sun and looking for any rings that might show up with that illumination. And rings around a tiny object like this may sound crazy, but we actually know of one other Kuiper Belt object and another object originally from the Kuiper Belt that do have rings. And so anything is possible out there in this very unknown region. We're also looking for any gas or dust that's coming off Ultima. We don't expect to see this at all. But comets do show this kind of behavior, and this is a spectacular image of the comet CG taken by the Rosetta spacecraft, showing these spectacular plumes of dust and gas streaming off from it as it's heated by the sun. Because Ultima has been in the same orbit for 4 billion years, any gas that would have evaporated has probably evaporated long ago. But this is unknown exploration. Anything is possible, and so we're doing our best to look for even these rather surprising and unusual possibilities with the observations we're taking. So we're making ultraviolet instruments, and we're taking images, backlit images, to look for this kind of thing. We are starting to learn about the shape of it, and I'll show you in a minute our first clues on that, but we don't know very much up to this point. We have the shadow of Ultima as seen from its passing in front of a star in a effort that was actually led by Mark Bowie again, to get some idea of its shape. And we see those two red circles give some approximation to how we might explain the shadow that we saw from those observations. And that might mean it's two objects that are orbiting around each other. And as we've got closer, we haven't seen evidence for that. But we still have to get the really close-up images to be sure. Or it could be a single object that is elongated. It could be a couple of objects that are stuck together and are resting on each other, kind of like the artwork you've been seeing here. And so we'll find out soon enough, and I'll show you some clues already that we have. We don't know if the surface is going to be covered in craters, which we might expect, but there's some recent ideas that, no, we may not actually see craters here because things don't run into each other very often in the Kuiper Belt. We might see evidence, like again on Comet CG in the middle there, of sublimation where gas and dust has left the surface and left holes behind. Or we might see something really crazy. This is, on the right is a picture of Saturn's moon Helene, no relation to our project manager, which has this crazy eroded surface. And so anything is possible out there when you're exploring a new class of world you've never seen before. And so the images that we're getting in the next couple of days, and we'll be hopefully showing to you coming up, are our first images that show any kind of detail we got down last night. I'm going to show you those in a moment, but don't get too excited. Then tomorrow we'll be showing images that show more pixels, about 6 pixels across, will give us some idea of the shape. And then, if everything goes smoothly, on January the 2nd and the 3rd, we will have more detailed images where we'll begin to see features on the surface. What you're seeing here are simulations pretending we were looking at Mars's moon Phobos, which probably looks nothing like Ultima, but it gives us something of about the right size and shape that we can use as a substitute here. And so that gives some idea of the kind of detail we're hoping to see in the next few days. And now I can show you the real version of that image on the left-hand side, which is what came down last night and has already got us very intrigued. And here we go. So the image on the left is the images as they came down from the spacecraft. It's a blob, only a couple of pixels across. But you can see just from that blob that it's an elongated blob. It's not round. And so we're already seeing that there's some interesting shape to this thing. And this is somewhat consistent with that shadow that we saw from the observations from the Earth. So that's not too surprising. But now this is just the first glimpse of what's going to get rapidly better from here on. When we sharpen up that image, we see that indeed it's quite an elongated object, maybe twice as long in one direction as it is in the other direction. So this is just our first taste. We're going to learn more very, very soon, and we just can't wait. So thank you.
Thank you guys for that overview, too. I never saw a team get so much out of a dot, right? We've been doing for so long. Before we move on to the questions, though, Alan, I believe you had something else to share.
Yeah, I do. Thank you, Mike. As you might imagine, I'm getting a little extra email this week. Overnight last night, I received one email that I want to read in its entirety. It's from Dr. Thomas Zurbuchen, my colleague and friend who directs NASA's entire science enterprise and runs the Science Mission Directorate. So let me read that to you. It's 3 paragraphs. He said, Alan, as you know, we are on government shutdown and I am unable to contribute to this historic event like I intended to. I will be sure to be there tonight, though, with my family, and here's why. I think that it is fitting that this flyby of Ultima Thule is at the interface of the 60th anniversary of Explorer 1 in 2018 and the 50th anniversary of Apollo 11 in 2019. To me, this milestone of New Horizons is full of everything NASA and NASA science is all about. It is about boundless aspiration and hope that are the inception of exploration. It is about innovation and persistence and perseverance to actually create the success by an amazing team that transcends what is reasonably expected, or even what seems initially possible. And then it is about surprise and transformative learning that has been at the heart of NASA and NASA science and exploration during the past 60 years. The Ultima Thule flyby has all of these. For all of those reasons, I wish you and your team the best of luck. We at NASA Science are incredibly proud of you and your team, both the science team and the engineering team, and we can't wait for the surprises that will be uncovered during the next hours and days. Go New Horizons, go exploration forever. Thank you. Thank you, Thomas. Now I hope that, I just hope that Thomas doesn't mind me reading his email to the world.
Thanks. So with that, we will go to questions for the media assembled here. I know a lot of people are following online too. So if you are following along with this mission on social media, we are on nasa.gov, and we are also on pluto.jhuapl.edu with the hashtags Ultima Thule, Ultima Flyby, and Ask New Horizons. We'll take questions first here in the audience. I know if the media, if you have a question, we have people on the aisles that will hand you the microphone. If you could identify yourself before you ask your question, and then we'll move on to the next ones.
Hello, Marcia Dunn, Associated Press for Dr. Stern. You've referred to this as auspicious beginning to the new year. Could you sort of elaborate on how you see this fitting into the exploration history of the world, most significantly 50 years after astronauts, flew to the moon and almost ready to, come up on the Apollo 11 anniversary? How it all fits together in your mind?
Sure. Thank you for the question. One of the things that distinguishes human beings from all of the other species on Earth is that we are so inquisitive and that we are naturally explorers. And I think space exploration really typifies that attribute of human beings. It's amazing to think that we as a species are interested in the rest of the universe and that we actually go out and explore it. And I'm very proud of our time and all the countries on Earth that are becoming involved in this historic enterprise. 50 years ago, the first humans walked on another world, the moon, as a result of NASA. And NASA was actually the first space agency to reach every planet in the solar system, from the closest planets, Venus and Mars, to the farthest, Pluto. And now we're out exploring even farther. And we put all the data in an archive where anybody in the world can see it. We don't keep it to ourselves, we share it. And I think that the kinds of things that NASA's doing are the envy of the world. And they go down in history, and they really set the United States apart as a leader. And I'm very grateful for all that.
Hi, Bill Harwood, CBS for Alan. What can you learn, some specifics about what can you learn about studying a cold classical KBO that you can't reverse engineer from looking at an asteroid or a comet closer into the sun? In other words, what is it that's frozen in time that's going to tell you so much about the formation of the solar system?
Yeah, I'll take a cut at that, and I think maybe John Spencer might also add a little bit. But there are really two attributes of Ultima Thule that make it so scientifically valuable for us. First, because it's so far from the sun, and the sunlight is so weak out there, temperatures are down near absolute zero. And as a result of that, chemical reactions are essentially frozen. So the object is in such a deep freeze that it's perfectly preserved from its original formation. And when you combine that deep freeze with the fact that Ultima is a small body, only tens of kilometers across, and can't have a strong geologic engine, like Pluto, for example, which is also cold, but which you can see the activity on its surface and in its atmosphere. Ultima doesn't have the ability to evolve that way. So everything that we're going to learn about Ultima, from its composition to its geology to how it was originally assembled, whether it has satellites and atmosphere or those kinds of things, are going to teach us about the original formation conditions of objects in the solar system that all the other things that we've gone out and orbited, flown by, landed on can't tell us, because they're either large and they evolve, or they're warm and they've evolved for that reason. Ultima is completely unique. John?
I'll just add a little bit that it's part of this structure, as you mentioned, called the Cold Classical Kuiper Belt, which is a remarkable structure. We have small bodies scattered through the solar system. We have the asteroid belt where things have been really stirred up, particularly by Jupiter. They've crashed into each other, broken into smaller pieces. Everything is very mixed up and not in its pristine shape there. And we have comets, which, as Alan said, have been altered a lot by the sun's light. But out there we have this belt of objects that are in almost circular orbits, that are flat orbits, the same plane as the planets. They have to have just, nothing has happened to these things since they formed. It's the only small population in the solar system, the only population of anything that we know of in the solar system, where virtually nothing has happened in the last 4 billion years. And so it's a very special region that we're very excited to explore.
Next question here.
Hi, Ken Chang, New York Times. I was just wondering how everyone's feeling now versus 3 years ago at Pluto. Are you more relaxed and confident because you've done it at Pluto, or is it still tense because of all the challenges that Alan was talking about?
Who wants to take a crack at that? I can tell you that we're very confident in the spacecraft, and we're very confident in the plan that we have for the exploration of Ultima. But I'd be kidding you if I didn't tell you that we're also on pins and needles to see how this turns out. We only get one shot at it. It's nothing like this has ever been done before. And with any enterprise like this, there comes risk. Fortunately, the rewards are worth the risk, but there is risk to the spacecraft and to the science that we're trying to do. And I think by tomorrow morning, we'll know how it all turned out, so stay tuned.
Hi, I'm Alan Boyle with GeekWire. Based on that first image, and perhaps you've had a chance, I don't know, to look at the fail-safe imagery, I realize it's too late to make any sort of change in the flyby maneuver, but is there anything that this image tells you about what you'll be looking at? Does this kind of definitively say that it's an elongated object rather than two or more smushed together objects? What does this tell you?
John?
Yes. I think it's a little early to say. We know it's not round. We can say that with confidence. But yes, this is not inconsistent with it being two smushed together objects like the artwork that we've been showing, which we just don't have the detail to see yet. It could well look like this right now, but we will know very soon.
Alan, hang on to your hat. I have to say, I said to the science team last night when this image first came in, I'd never seen so many people so excited about 2 pixels.
But we've had only 1 pixel for so long.
Okay, I think we have some questions over the phone too, so let's take one of those.
We have a question from Keith Cowing, NASA Watch. You are unmuted.
I actually had 2 questions to ask, but after hearing the email from Thomas, I'm going to ask the second one for Dr. Stern. You're going to have a spacecraft that is filled with fuel and obviously working rather well. Even if you're going after another Kuiper Belt object, you're going to have a lot of capability left over. Has any, and this is a way out question, but has anybody given any planning thought to a recreation of the pale blue dot image, albeit with a far more capable spacecraft and a little more time to plan it?
Yeah, so what the question is asking is whether New Horizons can reproduce the solar system portrait that Voyager took almost 30 years ago. In fact, we think we have the capability to do that, but it comes with some significant risk to the cameras because the planets are so close to the sun in angular terms, as seen from New Horizons. Taking that image runs the risk of burning the cameras out and actually permanently losing the cameras. So we don't want to do that until we're finished with all the flybys that we can possibly get out of this mission, and we do have an ambition of looking for another target after Ultima. So any image like that, which we very much want to take, will be years in the future.
Okay, I think we have another phone call. So I think we have another question over the phone.
Yeah, we have a question from Alexandra Whitby from Nature. Not there.
Okay, we can wait for that one. If we have any more questions here in the audience, let's go back to the audience first, and then we'll wait to see if we have the phone straightened out.
Up close. First, congratulations and good luck, all of you. Based on that first image and what you said about the no geologic engine, can you talk a little bit more about what you might expect or speculate on the surface of craters versus it being smooth or being something completely different? What are you thinking to this day? Thanks.
Well, I don't make predictions. I've seen too many of those go down in flames, and anything that I said today will almost certainly be wrong tomorrow. But I can tell you what we're interested in, and I'll give you one particular example for myself. We want to understand how objects like Ultima were assembled. There are two basic theories for how the building blocks of planets were assembled. In one case, you put objects together piece by piece, and in the other theory, they're built by sort of a hailstorm of pebbles and boulders and other kinds of particles. And depending upon whether we see a heterogeneous object or a monolithic object, we might be able to find out which of those theories is correct. John?
Yeah, I maybe say a bit more about the issue of cratering. Most small objects in the solar system have a lot of craters because they're old, they're not having geological processes that are erasing those craters, so they just accumulate scars from other things running into them over the age of the solar system. But a paper just came out that looked very carefully at how often Kuiper Belt objects run into each other. And it's not very often. There are hundreds of thousands of them, but they're spread over an enormous region of space, and they're all kind of cruising along in the same speed, in the same direction, kind of like on a freeway. And like on a freeway, fortunately, collisions don't happen very often. And so we may not see many craters at all. That would be a really interesting result. And if it's true, we might learn about the surface before it got covered in craters that would have been erased on other objects. So that's just an example of how little we know right now, and the kind of ideas that are out there as to what we might find. And yeah, we'll know very soon.
Okay. Let's do another one in here, and then we'll see if the phone line is open.
Stephen Young with Astronomy Now. Alan kind of hinted that the science team was excited by these 2 pixels, but I'm wondering if you could, either you, Alan, or John, say whether the science team has moved in any different directions with their conversations, speculation, interpretation, since they've seen this image?
John?
There's a lot of chatter in the science team room, and we're doing everything we can with so little information. It's kind of crazy because we're just so excited by this. But we know anything we say is going to be wrong tomorrow. And so ask us tomorrow, and then we may put you off another day. But we'll have much better images in a couple of days and these will be irrelevant at that point. So we're having a lot of interesting conversations, but we'll probably be wrong about them. So we'll wait until we know more.
Well, I'll just add one thing, and that is, after 3.5 years of planning for this, it's becoming very real all of a sudden.
Okay. We can stay here for a couple more questions, too, if we have them.
Hi, I'm Stephen Clark from Spaceflight Now. I was wondering, in the last day, have you been able to sort out anything about the rotation rate of this object? I know you've been searching for that for weeks, and you haven't been able to find anything. Any news there?
Right. So as background, by taking repeated images over time, we can see how the brightness of Kuiper Belt objects vary. And we've been doing this for years now as we cross the Kuiper Belt and studying the rotation periods of a whole suite of different Kuiper Belt objects. The only one that hasn't yielded a clear light curve is Ultima. What's up with Ultima? We don't know. And here we are now just, 10 hours from a flyby, and we still don't have a reliable light curve. We will find out why that is in the next 24 hours.
Give us another one in here.
Thank you. Tarek Malik with Space.com, and I think this question is for Helene. You mentioned in your talk that it'll take something like 20-odd months to get all of the data from this encounter back, and I know there was a similar kind of a year-long or plus for Pluto, and I'm wondering, kind of how that data is prioritized. Why does it take so long to kind of get so much data from what is essentially just a few hours of glimpsing before you shoot on by like a bullet? Thanks.
Sure, thanks for the question. So the data downlink, we're not just taking data coming down from the flyby, but we're also making observations of other distant Kuiper Belt objects along our trajectory, or that are not along our trajectory, that are from a distance. So we have to get that data down as well. And the prioritization for the data downlink comes from the science team led by Alan. You know, they let us know what's most significant, what they'd like to see first. And also we have housekeeping data that lets us know if, you know, ensures us that confirms that the spacecraft and its subsystems are healthy and flying safely.
You know, I'd like to add, I am in awe that we can even do this. The technology that's involved is incredible. The spacecraft has a 15-watt transmitter on it. 15 watts. It's a quarter of a light bulb. You know, not 15 kilowatts like a radio station, 15 watts, and we're receiving it from 4 billion miles away, these incredibly weak signals. And the fact that we can send data back at 1,000 bits per second, given those challenges, is unbelievable. And, you know, when you combine that with these advanced scientific instruments that take data like a fire hose and put them in the flash memory on board the two computers, where they're stored, we completely fill those memories to the extent that the engineers will let us, and then trickle it back at that 1,000 bits per second. And remember, we have to share the deep space network with all the other missions that NASA's flying across the solar system. So the combination of all those things together spells out 20 months.
Okay, so now so that we have a phone question.
Yeah, hi, this is Alex with Nature. Can you hear me?
We got it, Alex, yep.
Great, thanks. I wanted to ask John to talk just a little bit more about shape, this elongation that you're seeing. How is that consistent with the results you were seeing from the occultation studies earlier this year? And what, if anything, does it say about if this is a multiple object kind of squished together, whether you might have 2 or 3 objects smushed together?
Well, yeah, we've been having fun playing games, taking this fuzzy blob that we're seeing in these images and comparing it, sort of superimposing it on this intriguing shadow outline that we got from the occultations last year. And it fits pretty well. There's a lot of leeway in that occultation shadow because we only have a few points on it. And there's also a lot of leeway in this fuzzy blob, obviously, because it's so little information. And the hints that we had of 2 bodies in the occultation, I think it's safe to say we still are consistent with that. We'll just have to wait just a few more hours to confirm that. But I'll actually point out one intriguing thing, and I need to borrow Fred's pen for this. So as Alan mentioned, we haven't seen a light curve. And if it's elongated, as it appears to be, it wouldn't be as elongated as this pen, but if it's spinning like this, sometimes you'd be seeing it broadside on, and sometimes you'd be seeing it end on, and you should see a lot of variation in brightness, and we just are not seeing that. So our current best theory is that it's actually spinning like this. And so though it's elongated and it's spinning, we're always seeing the same side. And so that's our current best theory, and again, that might be proved wrong tomorrow.
Okay, we got one more question here in the audience.
Kelly BD Sky and Telescope, hi. So given that your hope is that this is the most pristine possible surface, which of the experiments offer you the best chance to actually determine the composition of what you're seeing, especially if it turns out to be dark and red? Do you have some hope of, you know, gases being liberated, whatever, Pepsi, I don't know.
John, you want to take it? Or you want me to?
Okay. I'm really interested in the color pictures that we're going to get because the Kuiper Belt is really intriguing in its colors. We have a variety of objects that are very bright, like Pluto. We have smaller objects that are kind of grayish colored, and we have other objects that are red or brownish in color. And we don't understand at all why there's this variation. And the cold classicals, this very flat circular belt of objects that that Ultima is part of, all seem to be red. Other parts of the Kuiper Belt have gray objects and red objects, and all these cold classicals are red. And that's really intriguing. It's a really important clue as to what's happening out there. And so by looking at the one object close up and seeing how maybe color varies across its surface, maybe it's brown, but it has gray craters, or who knows what. We might get some clues to what this big mystery is about the colors from that. But again, it's all speculation at this point. And it could be that the biggest clue is going to come from the infrared spectra that give us the surface composition. It could be that the best clues are going to come from the close-up images from our telephoto camera that will show us the craters, and the morphology tell us something about the history of its surface. Well, we just don't know yet, and that's what makes this so fun.
Because we had a little hiccup with the phones, I'm going to go one more time, because I understand we have another call in the queue. So one more question from the phones. Okay, this is Keith from NASA Watch. Go ahead.
Yeah, Keith Kelly, NASA Watch once again. And here's my other question. This is a bit like, with the speeds that you're talking about here, this is sort of like Star Wars TIE fighters flying over the Death Star. And I was just wondering, given that it's the proverbial bullet going after a bullet, is there any interest, or has there been any participation on the part of the Department of Defense? I know APO has some contracts with DoD, and there are precedents like the Clementine mission, which did seek to track things, and oh, by the way, they used the moon to practice with. So again, the question is there any DoD involvement with this? If there hasn't been, will there be?
Let me give you a very precise answer, no.
All right, well, thank you for those questions there. I'll give you guys the opportunity. Any concluding thoughts from the panel?
Great job.
All right, we're good.
Really nice, Fred.
All right, so thank you for joining us. I will advise you, like our spacecraft, our schedule moves quickly. So keep following us online at nasa.gov and at pluto.jhuapl.edu. Follow us on social media with the hashtags Ultima Thule, Ultima Flyby, Ask NASA, and Ask New Horizons. We have several other opportunities and events coming up. This evening we are going to have a Ask the New Horizons team online. Plenty of activities tonight of speaking and team members giving overviews and background on the mission itself. And then, wait, just after midnight, we'll have the debut of a song, New Horizons, from Brian May, contributing scientist, New Horizons science team member, astrophysicist, and oh yeah, guitarist for the band Queen. And then at 12:33 a.m., we'll mark the moment where New Horizons will be flying by Ultima Thule 4 billion miles from home. So thank you for joining us. Keep flying with us and keep exploring with New Horizons.
Gentlemen, please take your seats. The program is about to begin. Take your seats. The program is about to begin.
Welcome back. After offering the media a chance to ask questions of the New Horizons team, now it's your turn. For the past week, we've been asking social media followers to post questions on our Twitter and Facebook pages. We also asked you to write your questions for the team before you entered the auditorium. We'll select questions from both groups and pose them to the team members, Dr. Alex Parker and Dr. Kelsey Singer, both co-investigators from Southwest Research Institute, and Gabe Rogers, the New Horizons Deputy Mission Systems Engineer from the Applied Physics Lab. And helping us moderate the discussion is APL's Social Media Manager, Jessica Tozer. Jessica, over to you.
Hey, everybody. So you have asked your questions. Now we're going to answer some of them. One of the biggest questions we've been asked on social media in the last few days is why Ultima Thule? Why was this object chosen, and how was it chosen?
I can start with that one. We found 2014 MU69 in a search done by the Hubble Space Telescope in the year 2014. That's where that designation comes from. That search was a culmination of many years of effort. We started with ground-based observatories and moved to space-based observatories only when it was demonstrated to be absolutely necessary because the dense star fields and the direction that the spacecraft is traveling made it very difficult to find moving objects in the foreground, faint moving objects like 2014 MU69. We had conducted, over the course of the survey, we had made, we discovered about 50 other Kuiper Belt objects in addition to 2014 MU69. And before we conducted our Hubble survey, none of those had been actually targetable by the spacecraft. But they were close enough to the spacecraft that we can make long-range observations of them. Once we got the Hubble data, we found another 5 objects that were much closer to the trajectory. There were a few of them that were close enough that we could probably reach them with the spacecraft's remaining fuel supply. But after balancing all the benefits and risks and costs in terms of fuel and resources on the spacecraft, 2014 MU69 provided the best science return while minimizing the amount of resources that the spacecraft need to reach it.
That is great. And it's speaking of this object and its interest, a lot of social media questions have been sort of like, you know, what is this and what do we know about it? And so we got a question about the shape and orbit period of Ultima Thule. Do we know anything about that?
At this point, the information that we have on the shape mostly comes from observations we made here on Earth, the occultation observations that you've heard a bit about earlier, and you'll hear more later today when Mark Bowie speaks. give us a rough outline of its cross-section in one moment of time. And so from that cross-section, we have this idea that it is probably not a very simple shape, that it's at least elongated, maybe bilobate, possibly a close contact binary. We'll definitely know soon as the data from New Horizons improves and absolutely exceeds the resolution, the data that we got from the occultation. Its orbit is 298 years long. It takes 298 years for it to circle the sun one time. So it's much further out from the Earth. The sun's gravity is much weaker there, so it takes much longer for it to orbit the sun. That orbit is very, very circular compared to the orbits of other small bodies, and it's very low inclination, meaning it's close to the orbital plane of the planets. So it's in this very special region of the solar system that we've been talking about, the called classical Kuiper belt, this very thin disk, very circular disk of material at the edge of the solar system. And that's about what we know about its orbit and shape at this point.
All right, let's move on to a couple of questions about the spacecraft in particular. One question that we got, especially from some school-age kids from Kansas, is how fast is the spacecraft now traveling?
So the spacecraft is now traveling about 14.4 kilometers per second relative to Ultima Thule. Basically, it's moving so fast that we're only at closest approach for, about plus or minus 1 hour on either side of it. And it's moving fast enough that ultimately it's going to go out of the solar system and continue on.
Oh,
I was going to say too, something that I learned recently is that's about 30,000 miles per hour. So hopefully no one's ever driven that quickly down the highway, but it's a very speedy spacecraft.
I think it'd have to be. And so now that we're talking about some deep space stuff, I want to transition to a question that's what lies beyond the Kuiper belt? We only really know the Kuiper belt existed a little while ago, so what's beyond that?
Beyond the Kuiper belt are a number of other structures in the outer solar system. This idea of the Kuiper belt is really typically applied to just a few structures in the outer solar system, the cold classicals that we're flying through, this sort of scattered disk of material that interacts with Neptune continuously, things between sort of Neptune's orbit and a few times further out than that. But if you get beyond that, you get into other more distant regions, often referred to as the Oort cloud. And sometimes the Oort cloud is broken down into different subregions, like the inner and outer Oort cloud. The Oort cloud is the sort of source population for most of the really long period comets, the comets that we've only ever seen one time as they sweep through the solar system and go out and disappear into the darkness. It's thought to be more of a spherical swarm of material that was ejected very early on from closer to the sun by the migration of the giant planets after the giant planet formed. They didn't form exactly where they are now. They moved around a bunch before they settled into their final architecture. That motion kicked things up, stirred things around, and pitched a bunch of stuff out into space. Once things get out far enough, the rest of the galaxy starts to matter. It starts to reach in with its tenuous gravity and grab hold of things and lift them even higher very, very slowly. And so you isolate them in this very distant swarm of material. Right now, we have no plans to go and explore this population because it's so far away, hundreds of times, if not thousands of times further away than MU-69 is. And so if we were to take a mission like New Horizons and try to go to one of these objects, it would take thousands of years, if not tens of thousands of years. So for now, we have to try to explore it remotely using our observatories, telescopes, and using techniques like occultations to probe it. But perhaps in the future, if we can engineer much faster spacecraft, we could push on further and go out and explore the Oort cloud.
Space is really big. So this question was the most asked question on social media, so I think we should definitely get to it, and that is, how are you able to communicate with a spacecraft that's 4 billion miles away?
So basically on board the spacecraft, we have a high gain antenna, and we are able to transmit to the deep space networks, which have 70-meter antennas. And there's 3 different stations scattered around the United States, so we could always communicate with one of those stations if we needed to. It takes about 30 watts of power on board the spacecraft to talk about 4 billion miles back to the Earth.
And so basically, and then the other question was the downlink. How long does it take to receive signals, photos, things like that? You know, so people are saying it could take years, but
yeah,
it doesn't.
right now it takes light about a little over 6 hours to transmit from the spacecraft to the Earth. And even with all of that distance, we're able to get about 1,000 bits per second. So that's why it takes about 16 hours for us to downlink the images from a single observation pass in order to see it.
It's like using a modem in the 90s.
Yes, it is.
Yeah.
Except there's no dial tone.
Kelsey, this is a question I would hoping you would answer, and that is, what are you hoping to find out during this flyby? What are some things that you're really looking for?
Great question. So, I mean, we're going someplace we've never been before. I'm expecting to be surprised, but since I do mostly geology and geophysics, a lot of the things I'm looking for are what kind of features are on the surface. Do we have cracks? Do we have faults? Do we have craters? Do we have features we've never seen anywhere else in the solar system? I would not be surprised if we find some. We're also looking to see, does Ultima Thule look like a comet? Does Ultima Thule look like any of the moons around some of the giant planets? And we're going to be comparing what we find to learn more about all of these objects as a whole.
Which is an incredible thing, since we've never had the opportunity to really explore a Kuiper Belt object ever before.
For sure.
What is so significant about the Kuiper Belts in regards to science? Like, why is that important for us to better understand?
I can give a start to that and see what my colleagues here have to say. But we believe that Ultima Thule, as has been mentioned, is what we call a cold classical Kuiper Belt object. And the cold does not refer to its temperature, although it is very cold out there. It refers to the orbit that Alex was talking about. And we think it's been sitting in this orbit, in this distant place in the outer solar system for most of its life. And so it's a unique piece of the early solar system that hasn't had, we think, a lot of processing happen to it. And it's not every day that you're able to go to a piece of the early solar system and learn about that point in time. For example, on Earth, we have lots of geology going on, and that erases a lot of the signatures from earlier in time. So we're really hoping that that piece of the Kuiper Belt that we're going to right now will help us learn about how the solar system formed.
Yeah, I think it's really important to recognize one of the, there's words like primitive and pristine and ancient that are used a lot to describe things like the cold classical Kuiper Belt objects like 2014 MU69. And the thing is that most of the things that we go and visit in space can be described that way in one way or another. And one of the things that really makes the way that we're talking about the primordial nature of MU69 is that it can be linked directly back to where it formed. Almost all the other populations that you see, the asteroids and small bodies, and even the planets themselves, they didn't necessarily form where they live today. So if you want to take what you learn about an object and try to back out what the environment in the solar system was like in a particular location, try to understand the processes that were at play, that were building the planets, you have to bring in all this other information to try to work out where that object actually grew up. And a lot of that is model dependent. It requires you to make inferences about what everything else was doing, and it's a big puzzle. And one of the nice things about the cold classical Kuiper Belt is that, as best we can tell, it formed exactly where it is today. And so if you want to link properties of somewhere in the disk to the primordial disk that formed the planets to a population of objects that we see today, that is most easily, clearly done by going to the cold classical Kuiper Belt.
So this kind of leads to a different, goes into another question, and that is about the distance. So we're going to get so much closer to this object than we got to Pluto in 2015. Why was the distance chosen for this object?
Flyby distance.
So we were trying a few years ago to decide what the optimal distance was going to be that the spacecraft could easily do from basically a hardware standpoint, but also give us the best and optimal science. Obviously, we could get a lot closer, but if you do that, you get higher resolution images, but only for a very short period of time. And then the phase angle, basically the angle between the sun and the spacecraft wasn't as good, so you couldn't see a lot of the wonderful craters and stuff. If you get further away, you're actually able to take more images. You're able to scan over the uncertainty ellipsoid a lot more. However, the resolution is not the same. Then there was the question of, do you fly ahead of the spacecraft, or ahead of the body? Do you fly behind the body to try and get an occultation like we did at Pluto? Do you fly north? Do you fly south? So the scientists debated, and they ultimately chose the aim point that basically optimized the scientists for all the different instruments.
And here's another spacecraft question, and that is, how does New Horizons continue to sustain itself even though it's so far away from the sun and hurling through space?
So we are carrying essentially right now about 190 watts of power provided by plutonium in an RTG. And that also provides heat for the spacecraft. So the spacecraft is essentially like a thermos bottle, and it's being heated by the decay of the plutonium. That decay basically creates all of the power that we need to do to fly the spacecraft, to communicate back with the Earth, to run all the onboard instruments, and basically to take the images as we fly by. This power degrades over time. So every year we get a few less watts of power, so we have to get creative in how to maintain the spacecraft as we get further and further away from the Earth.
Is there a distance where you would no longer be able to communicate with New Horizons?
Yes, there actually would be a distance. Because we've only got about a 30-watt transmitter through the high-gain antenna, the further away we get, the lower the data rates get. And at some point, we would get far enough away that we wouldn't be able to get data rates that would reasonably be able to play back images. But we expect by the time that that happens, the plutonium will have actually decayed to a point that the spacecraft would start to be too cold in order to keep itself warm. The hydrazine and the fuel tanks would freeze. And that's probably what is going to be the end of life for the spacecraft, not the communications distance.
And that's going to be mid-2030s?
Mid-2030s.
It'll be a cold death, but at least we'll hear about it.
Yes.
So optimistic.
Yeah.
It's going into cold storage.
Yeah.
Yeah.
So what do you think is next for New Horizons? Just going to keep on going then, yeah?
Well, we have a couple observations already planned that will be executed on the spacecraft, looking at more of these distant Kuiper Belt objects that we discovered in our earlier surveys. These will be more of these long-range observations that we've been doing, trying to look at their surfaces from a unique vantage point, actually looking back at them toward the sun, not as close as would be required to look at the Earth per se, but by looking back at them like that, we can see light that scatters off of diffuse structures like, say, rings. So we have some objects after Pluto, or sorry, after 2014 ME69 that we're already planning. We've conducted some observations using the CTIO Observatory in Chile and their dark energy camera, which is this wonderful new instrument that covers a lot of sky, to go and actually look for some new targets that are even further from the sun than 2014 ME69, things that we could target at long range from the spacecraft between 2019 and 2025, for example. The reason why we have to do these searches now and we don't put them off is because the earlier we can find these things, the earlier we can define the requirements for them and make our plans. The earlier we make those plans, the fewer resources they require on the spacecraft. So we really have to front load everything like that.
I was going to say, also, I mean, we're obviously also going to try and find another target to do a close flyby of. It's a pretty low chance, but it's worth a look, and we're going to use instruments on board the spacecraft as well to try and do that.
Yep. We've been very careful about managing the onboard resources, the consumables like propellant and thruster cycles, all through this extended mission. So we have been able to keep a little bit of extra propellant in the tank in case we do find another object down the road. And so we're always keeping that sort of monitored closely.
All right, we're going to take a couple questions from the audience here today. One of them is, what matter composition do you expect to find in Ultima Thule?
Oh, yeah, that's a great question. We don't have a lot of constraints on the composition already. So it, again, we'll be learning a lot with the instruments on the spacecraft. And we'll be able to look at the overall color of the object, and that can tell us about composition. And we also specifically have an instrument that measures in different wavelengths in order to get a signature of the composition. So we could find some different types of ices. We might find water ice. We might find more what we call exotic ices that only form in very cold places. We don't have these kinds of ices on Earth. Things like we found on Pluto, methane, ammonia maybe. And then there's also something that's making it dark. And we don't know exactly what that material is. So we'll be checking that out.
Yeah, this is one of the things to recognize about these objects is that they're very far from the sun, so they're very faint when observed from here. And they have these dark surfaces. They're, look like asphalt in terms of how dark they are. What we do know about their compositions a priori going into this come from remote observations done from the Earth. And so there's only a limited number of things we can tell from this kind of distance and with these kinds of faint targets. And 2014 MU69 is the faintest of them. There is no fainter object that we've tracked and studied to this detail anywhere. And so it's really been one of the most challenging ones to describe ahead of time. But what we know from studying objects that have moons, which can tell us about the mass of the system and the size of the objects in the system, is that they're probably mostly made of water ice. They have a density, their bulk density is comparable to that of frozen water, and that there's other minerals mixed in. There's been some indication that there are silicate minerals present in Kuiper Belt objects. And larger objects can hold on to more things because things that tend to evaporate, these exotic ices, which we'll hear more about later today, they're easier to be held on to by larger objects. So things like Pluto could have all sorts of exotic ices on it, but something as small as 2014 MU69, it will be a lot more surprising to see some of the more really, really volatile compounds. So if we see them, we'll know that there's something kind of unusual going on.
And in the vein of exploring strange new worlds and seeking out new information, what is the significance of the circular orbit?
Well, the significance of the circular orbit, so the Kuiper Belt has many, many objects in it, billions of objects. And if you were to pick any one of them, they're going to have, on average, a more circular orbit than most other populations of small objects in the solar system. The fact that 2014 MU69 is really quite circular is probably just a reflection of roll of the dice. It belongs to this population. Some of them are really circular, some of them are not. We don't think that indicates anything particularly special about 2014 MU69 with reference to the rest of these objects that are members of its extended family. We don't think that necessarily means that it's even more pristine than something else in the cold classicals, but it does help us confirm, it really helps support the idea that it really belongs to this family of special objects.
It's good that we're exploring a special object. We wouldn't want a non-special object
No.
or something like this. How are you able to take pictures in space, especially since space can be kind of, you know, dark?
There's a lot more light in space than one would think. And the cameras that were designed for New Horizons were designed to work deep in space, far away from the sun. We actually took a lot of images on our flyby of Jupiter back in 2007. However, we had to be very, very careful there because all the reflected light from the sun at Jupiter was way too bright, and it actually saturated out a lot of the images. So now that we are out in the Kuiper Belt, we're actually in the region of space that New Horizons was designed for. We've actually developed a series of long exposure images. So in order to see MU69 early after we spun down in August, we developed a way for the spacecraft to take these 30-second exposures and really try and get down to get every little photon inside the camera. And you've seen the results.
I was going to say, we had an experiment, so to speak, at Pluto, where we tried to have people guess what they thought the light levels would be at Pluto, because Pluto is also very far. But it turns out it may not be as dark as you would think. It's actually about twilight time, dawn or dusk, and that's what it would be at noon on Pluto. But MU69 is much farther, Ultima Thule is much farther, and so it will be darker there. But as Gabe explained, our instruments are designed for this.
Yeah, it really helps to have big eyes. You know, if you go into the deep ocean, you know, the giant squid have eyes the size of a dinner plate, and New Horizons' biggest eye is about that same size. It's all about collecting as much light as possible.
Do you know if Ultima Thule has a magnetic field or magnetic poles?
I can answer that. There's still a lot of unknowns about how planets generate magnetic fields, but we do have some information that we think is necessary in order to have a magnetic field. And that usually requires you to have a melted or partially melted interior that has something that can conduct electricity. And in the case of most of the planets, it's iron. And it's relatively unlikely that an object as small as Ultima Thule has a melted interior or ever had one. It's probably mostly made of rocky and icy materials. So it's pretty unlikely that Ultima itself ever had a magnetic field. There's a very small possibility that it's a small fragment of a much bigger object. And in that case, maybe that bigger object had a magnetic field, but all in all, pretty unlikely.
So this object's pretty far from us, and sometimes a unit of measurement is an AU. And so one of the questions is, what is an AU, and why is it used to measure distance in space?
It is not the internet parlance of absolute unit. It is the astronomical unit. It is the average distance from the Earth to the Sun, and it is used as a useful yardstick. So if we say something is at 44 AU, it means it is 44 times further from the Sun than the Earth is on average. And one of the reasons why this is a useful tool for us is that it makes certain calculations kind of easy. If you want to look at how much something moves in the distance from the Earth moving back and forth, kind of like holding your finger up and closing one eye, then closing the other, and seeing things in the distance move back and forth from parallax, using distances that are in multiples of the baseline that we have, the Earth's diameter, the Earth's orbit's diameter, is really useful. So it helps make the math simpler and easier to do in your head, pretty much. So it's been around for a very long time. It's a great unit for scaling how bright things are, how long it takes to get places, how big something looks in the distance, and that's why it's hung around as long as it has.
And Kelsey, you answered this a little bit, but let's expand on this. Would you consider Ultima Thule a comet, a dwarf planet, something in between?
Good question. Yeah, so the comets are former Kuiper Belt objects that have been kicked into the inner solar system. And so they're not unrelated, but they're not exactly the same thing. Some people may be familiar with Comet CG, which the Rosetta mission went by. And that's about 4 kilometers or so across, whereas Ultima Thule is closer to 30 kilometers. So you can see there's a pretty big difference in size as well for what we've explored up close in the inner solar system versus what we're going to now in the outer solar system. So there is a relationship, but they're not the same. And Ultima Thule is a little bit too small to be a dwarf planet. But it's going to be an interesting object nonetheless.
Why would you consider this such a historic moment for space science?
I mean, this is the furthest exploration that we've ever done from the Earth. I mean, when we launched, we didn't even know that this existed. And now we're going to be, in a few short hours flying by this. 30 years ago, we didn't even really know all of the details we knew about the Kuiper Belt. We've learned about the third zone within, these last few decades and stuff. And now we've got a mission that's been traveling out there for 13 years, and we're on the cusp of exploring something that nobody's ever seen before. And that, for me, that's really exciting.
I'm really excited too. Do you think Ultima Thule is emitting heat, or could it possibly?
Pretty much everything in the universe emits some amount of heat. It is warmer than its environment. It is warmer than the cosmic microwave background radiation, and so it is emitting heat. Or rather, it has heat, it is warm, and it is emitting infrared radiation that we perceive as warmth, intangible warmth. And so one of the things that we'll be doing to measure that is using the REX instrument, the thermscan measurement, which allows us to pick up that kind of thermal radiation from a warm object. And when I say warm, it's close to absolute zero, but not so close as to not emit anything.
All right, last question for all of you, but don't answer simultaneously. And that is, why are you personally excited about this?
I'll start off. I mean, I've been on this program since nearly the beginning, at least as long as it's been here at APL. And so I've seen the development of this from basically a concept on a piece of paper all the way through INT, launch, the flyby of Jupiter, the flyby of Pluto, and now the flyby of Ultima Thule. So this has been a fascinating journey that I've been on for these past few years. I'm really excited to see what we find, because every time we find something new, it is fascinating. And so for me, that's why it's really exciting right now.
Go ahead.
Okay, yeah, I mean, it's hard to be going by a type of object that you've never seen before. So it's just great to be able to learn about this new place in the solar system along with everyone else.
For me, I've been studying the Kuiper Belt for the duration of my academic career this far, searching for objects in it, characterizing objects in it, but it's always been the kind of thing where I'm learning a little bit about a lot of objects, and there's never been this opportunity. So I have this sort of understanding and relationship with the Kuiper Belt as a whole, but there's never crystallized into a single object where I get to know a lot about one thing, and that's what we get to do with 2014 ME69.
All right, well, thank you guys all so much for being a part of this and answering questions from the audience today. If we did not get to your question today, that's okay. We are still going to try to answer questions on social media, on our Facebook and Twitter throughout the day from our experts who are far more knowledgeable than I am. And we're going to try and explore as many questions as we can as we seek all answers together. So thank you so much.
Thank you.
And now let's check in on the progress of New Horizons using NASA's Eyes on the Solar System as the spacecraft approaches Ultima Thule.
New Horizons is far out for its flyby of Ultima Thule, another billion miles beyond Pluto. As the spacecraft is doing its planned quick slew to point its antenna back to Earth, what is happening now, John?
Well, yes, indeed. We're now a record-breaking 4 billion miles from the Earth. And right now, the spacecraft is maneuvering so that it can scan the plasma environment around Ultima. It's got 2 plasma instruments, SWAP and PEPSI, that are going to be sampling the plasma flow in all directions around it. So to do that, the spacecraft has to do this barrel roll, a 30-minute turn, and it's pointing its main antenna towards Earth to be in the right position for that. We're not actually talking to the Earth right now.
Thanks, John. And this is New Horizons Now.
Ladies and gentlemen, for the next portion of this afternoon's event, we have 2 special programs that are going to occur in the dining area. The next performer will sound familiar to those of you who were here and with us for the Pluto flyby 3 years ago. You might remember his song, Hi Pluto. He's back, this time with a musical tribute to the Ultima flyby. Please welcome Craig Worth in the dining area.
Oh, that's me. Hello. Hello, I'm Craig Worth. I'm a singer-songwriter from New Hampshire and a big fan of science, of course, and New Horizons. And I did write that Pluto song, and then Alan asked me if I had any inspiration about the next leg of the mission, and I surely did. It's my job as an artist to compress all this science, which I don't fully understand, but I greatly appreciate, and the passion of people for discovery and for learning and understanding into a piece of art that touches hearts and minds. And with this song, which I'm going to invite you, unlike the Pluto song, this is a sing-along. So please, with whatever voice you have to offer, we could have 17 different notes, maybe 40 different notes. It's all good. It's all good. This song is about amazement. We can look around in our lives and find amazement at every turn. It's not hard to find amazement in something like this. And so this song is called I Am Amazed. And the refrain, I'm going to sing the refrain first so you hear it, and then I'll sing the song. Again, join me. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. The mission team sang it with me last month. More than 36 showed up to sing it after a long day, volunteer. It shocked the heck out of me. We'll show that video tonight, but for now, let's join him. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. Beautiful. Isn't it amazing how we learn to leave the ground? Isn't it amazing? The firing up, the counting down. Isn't it amazing when we passionately turn to all we know and hope to learn? It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. Isn't it amazing? All the ones who came before, isn't it amazing how they've opened up the doors? Isn't it amazing? Every woman, every man, on whose dreams and work we stand. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. Isn't it amazing? Oh, the science and the art, isn't it amazing? To catch the view of Pluto's heart, isn't it amazing? The wing our spirit flies on toward all these new horizons. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. Isn't it amazing? All this wonder that we share, isn't it amazing? How it reaches way out there, isn't it amazing? When we engage community, we can reach Ultima Thule. It's amazing. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. One more time. It is amazing, I am amazed. It is amazing, I am amazed. It is amazing, I am amazed. Thank you. Thank you very much. Thanks so much.
That was amazing. This is a special part of the program for our future explorers. Our next guest travels at the speed of thought, delivering information about the health, science, and history of this planet and many others. Please welcome Janet of Janet's Planet.
Hi, everybody. It is indeed a pleasure to be here. I had the good gift of being here at the flyby of Pluto. So happy New Year to everyone. And if we'll get my presentation up and running. So we have this opportunity to talk about exploration. And so do you have that yet back there? All right. As soon as we have the presentation good and plugged in, making sure we've got all of that happening. All right. Oh, good news. All right. Well, I want to talk to, especially if you're young, I don't know if you would be willing to come in and fill in some of these seats here and get super close to me. Thank you for some of you guys that I met earlier. We've been making some great things down in the building. In fact, one of the things I will tell you for sure that something I really want to show you is that we've asked the young people to show us a little bit about what they think Ultima Thule is going to look like. And I love this rendition by Bailey. Is Bailey anywhere in here? Oh, come here, Bailey. I want to introduce you then to the artist. And can you give her a big round of applause? And it will be interesting tonight to see if this happens to be what Ultima Thule looks like. So yeah, smile there for the camera. Yeah, there we go. You just may make the scientific prediction of the evening, my sweet. So again, I want to see if we got this playing. Okay, great. So Happy New Year to everyone. What we're going to first talk about is the thing that got us here is Hubble. Dr. Nancy Roman is called the mother of Hubble, and she was a Nashvilleian, where I am from, so I'd like to pay a little bit of homage to her tonight. But I also want to take us back to that moment just 3 years ago when it's like New Horizons actually lifted off.
We have ignition and liftoff of NASA's New Horizons spacecraft on a deck.
So today we're 12 years and 346 days later, and remember it sets top speeds, launch speeds going over 36,000 miles per hour, got that beautiful gravity assist from Jupiter, and was all of a sudden going 51,000 miles per hour, and then after 9 years, 5 months, and 25 days, finally revealed 11,000 feet ice mountains. Elsa would have had a great party, right, on all of that. So, and that beautiful Heart Mountain. So one of the reasons is that we're continuing further into this epic land of the solar system out there in those distant icy worlds is because of Hubble and the many explorers that have gone before. In Craig's song, we heard him say that it's like, who will you build upon? All of those geniuses are standing on the shoulders of giants. So what will Ultima Thule look like? We've been asking kids 6 to 18 that question. You saw my picture from Bailey. I have some others here that are really pretty awesome. This is from a group of 3rd graders. I don't know if you can actually see it, but it says from the love of children, and she thinks that Ultima Thule may look like lipstick, apparently. Also, this was a rendition. I think he was just representing all the kind of weird objects that might live in the Kuiper Belt. So, and then this I love. Simplicity is king, right? So just, that's what it could look like, just a little smiley face there. So we had a ton of fun trying to think about what is it going to look like. So we don't know yet, right? It could look like an upside-down Christmas tree, an aardvark, a weird crocodile head. We just won't know, and that's going to be the exciting buildup. And when we think about exploration, let's go back to little Ferdinand Magellan, the first guy to circumvent the entire world. He was thinking that it wasn't flat. He proved it right. It's round, and there he goes. And then we have, I don't know if you know this lady, it's one of my very favorite heroines of science, Mary Anning, the first female paleontologist. She was on the cliffs of Dorset and Limes Regis, and she was finding these amazing fossils and ichthyosaurs. Amazing. What a great explorer she was. And then we have Lewis and Clark, led by Sacagawea, and the core of discovery. Again, discovery and exploration just seems to be part of our DNA and why we're here tonight. And I would be remiss if I didn't say the first ladies of space, Valentina Tereshkova, the first Russian woman in space, Sally K. Ride, the first American woman in space, and then Mae Jemison, the first African-American female in space. And I bet some of you can find yourself up there. If you're one of those guys and gals that's a great explorer, give yourselves a big round of applause, right? So, because without you guys, we wouldn't be here. And I always love honoring Miss Alice Bowman, Mission Operations Manager for the thing. Amazing lady that she is. And all of those amazing ladies that are there and part of the principal investigation team. And I always love showing people there are happy scientists. Never, do not dismay. Do not think science is not the most exciting, most thrilling proposition of all, because whatever we know today could change tomorrow by something we discover at midnight. So that's why I love science. So, and you know, and it's fun to imagine about what we want to do. Here on Janet's planet, we travel at the speed of thought. And one of the things that Einstein said is that imagination is more important than knowledge. And so it will take us anywhere we want to go. So never, ever lose a holy curiosity. So for anybody in here who's wanting to continue to always love to explore, raise your hand. You ready to keep on exploring? Good. Because somewhere something incredible is waiting to be known, as Carl Sagan said. So here's what we're going to do. I'm going to teach you guys how to use your brain a little bit better. This is what I do in my shows that I travel with all over the country. And you put your fingertips right here on your temples. The most powerful computer yet built is still your brain, right? That's pretty exciting news. Your awake and alive brain could light up a light bulb if we simply could plug it in. That would probably hurt, so we won't try that. But right now, just tap it, shake your heads a little bit, get those neurons kind of moving. Whoa, that feels good, right? Waking everything up. It's already been an exciting day. We kind of hit that 4 p.m. coffee break kind of slump time, right? So I want us to wake up our brain. We don't use any kind of fuel other than the power of our thoughts to take us where we want to go on Janet's planet. So I leave no carbon footprint, everybody. So we're going to start with the star at the center of our solar system, the sun. It's a star like all the others in the night sky, only it's much closer. 93 million miles to be, in fact, 1 astronomical unit. Now, here's what's crazy. It's 109 times the diameter of Earth. You could fit over 1 million Earths inside the sun and still have room to spare. Wrap your mind around that even. Takes 8 minutes for the light from the sun to reach us here on Earth. Without its heat and light, life on Earth would not be possible. And at its core, it's a toasty 27 million degrees Fahrenheit. And just recently, Stanford kind of sampled the sound of the sun. Sounds like something we do in yoga class, right? Now, the Parker Solar Probe, talk about exploration. It's the first time we've had the technology to go all the way to the sun. It is going to be phenomenal. It's like it finally had the heat shield to keep all those instruments at a toasty 85 degrees. And we're going to find out even more about solar wind, why the corona is hotter than the surface. And you guys know, of course, this is solar flare. I'm going to ask you guys to go solar flare. It's like kind of scrunch down in your seats and give me a lot of energy. 1, 2, 3, get ready to go. Wah! 1, 2, 3. Wah! Oh, come on, you can go solar flare bigger than that. Here we go, 1, 2. I want to hear you loud, loud. We're about to go by a distant object. 1, 2, 3, loud. All right, so the next time your parents go, calm down, you can just go, I just had to go solar flare, all right? So that's any time with huge amounts of energy is suddenly released in a magnetic region. Now, I have prizes over here on this table. So prizes are for participation as well. So I want somebody to shout out what is the first planet we're going to come to in our solar system. Mercury. All right, I heard you. All right, so that earns our first prize for the day. So here's what you're going to do. Mercury's about 36 million miles from the sun. I need you to help me think travel there. So put your fingertips here. I want you to make my meter go all the way up to 11. All right, you ready? I'm going to need your thoughts. Come on, give them to me. Come on, yep, oh yeah. Make that meter go all the way up to 11. Just like in Spinal Tap, always goes to 11. All right, good job. Now, Mercury was named after the Roman messenger of the gods because he's so speedy and quick. It goes around the sun in just 88 days. And think of it like this. If orbits were racetracks, Mercury would win every single time. It's basically covered in lots of silicate material, is hugely cratered, and we'd never even seen pictures of it until Mariner 10, another great explorer, flew by between 1974 and 1975. Messenger was just there between 2012 and 15, and now what is really exciting is that the European Space Agency has launched something called Bepi Colombo that is going there again to find out more about this very, very interesting, eccentric planet. Now, here's where I'm going to need a couple of volunteers. I need somebody to be the sun, and I need somebody to be Mercury. All right, you want to be the sun? Yeah, you want to be the sun? All right, now I need somebody to be Mercury. All right, you're coming down to be Mercury. So it has one of the most eccentric orbits of all. So you're the sun. You're quite bright. What is your name? All right, Christoph. All right, so here's the sun. You are going to be Mercury. But Mercury has a very long elliptical orbit. It goes out wide and long, sometimes from 29 million miles to 46 million miles. And you also have to remember that not only do planets revolve around the sun, they also rotate on their axis. So can you get going there with a little rotation? Oh, no, we got to go over this way. You're way too close, Mercury. That's right. It's more oval. Yep, now. And then here we go again. Whoa, keep on. You're not rotating. It's like, come on, oh, it would have had to, all right, yep. And so that is a little bit of an explanation of how far and what, wow, like I said, Mercury's super fast. All right, let's give them both a big round of applause. All right, here you go, my dear. Thank you so much. All right, so if we're thinking like this, what then would be the next planet that we would come to? Venus, help me think travel there, come on. All right. We got another 30 million miles or so to go. Awesome. Now, well, apparently we didn't quite get there, so go again. All right. Oh, wow, we went all the way through. We got so far down there. Let's go again. All right, so there we are at the sun. That would be Mercury. Now let's try this for Venus. Space travel's trajectory is hard, right? All right, you guys gave me such good thought power. Nope. All right. I'm so sorry, guys. No, okay. I'm going to try one thing. I'm going to go over here. I'm going to do a little this. This is what we do when we make sure we've got what we need. And, all right. Venus, here we come. If we skip past Venus, we'll just have to skip past it today. All right, here we go.
Venus is the real Miss Universe of our solar system, named after the goddess of love and beauty. Quite exquisite, really.
Very beautiful, but you wouldn't want to live there. There's no oxygen, there's no water. And does anybody know how hot it is on Venus? How? Not quite that hot, but super hot is right. Do you know? More than 100 degrees, around 870 degrees Fahrenheit, my dear. And it's covered in these dense layers of clouds. And scientists believe that a lot of those clouds are caused by the release of sulfur dioxide gas from all of Venus's volcanoes. Now, the only few probes that went to Venus actually melted. I think the longest one lasted about 2 hours and 7 minutes. But again, because of those dense layers of clouds, as the sunlight hit it, it reflects light and shines back very, very super brightly. We consider it our morning and evening star. And if we could stand on the surface of Venus, it has much more a circular orbit. It's even hotter than Mercury because it has a substantial atmosphere with all those clouds. The sun would rise in the west and set in the east. Again, beautiful to look at in the night sky, but we really, truly would not want to live there. All right, so if we're thinking next in our kind of traveling here through our solar system, what's the next planet we'll come to? Earth. All right, here we go for Earth. And go. All right, let's try for Earth. Come on, help me think. Would you look at that beautiful blue ball? Home sweet home, right now to 8 billion people. By 2050, it's estimated that we'll be a home to 11 billion people. Hard to imagine. Also, the one reason we got to take care of this beautiful blue ball is that as the mountain glaciers melt, that the bulge at the equator is getting larger, but also get this, by 2050, we could have as much plastic in our oceans as fish. We got to do better. And as we are rotating on our axis at a little over 1,100 miles per hour, we're also orbiting the sun at a little over 67,000 miles an hour. Our world is 70% water. 80% of all life lives in our lakes, rivers, streams, and oceans. And this is the most fantastic fact I love. 99% of all the living space actually lives in our lakes, rivers, streams, and oceans. So again, as we take a look at this beautiful place we call home, time to take good care of it. And then we get the opportunity to have this lovely orb, the moon. Do you see a man or a bunny rabbit? I usually see the man's face. Take a look there. But in May of 1961, President John F. Kennedy commits the U.S. to something extraordinary.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
We choose to go to the moon in this decade and do the other things.
Not because they are easy, but because they are hard. And of course, that mission is called Apollo. We just celebrated the 50th anniversary of Apollo 8. In 2019, we'll celebrate the 50th anniversaries of all of those Apollo missions that led to Michael Collins, Neil Armstrong, and Buzz Aldrin leaving Kennedy Space Center on July 16, 1969, and 3.5 days later arriving at the moon. Neil noticed that the onboard computer was steering them dangerously close to this crater, and with 30 seconds of fuel left, he seizes control of the craft, leaving mission control nothing to do but just kind of watch and wait and worry. And with 20 seconds of fuel left, the craft touches down.
Listen, Tranquility Base here. The Eagle has landed.
Now, it would take him hours before he'd actually exit out that hatch, down that ladder, and say these very famous words.
That's one small step for man, one giant leap for mankind.
Then Buzz and he would capture and collect a lot of moon rocks full of titanium, and then Michael Collins would fly them home and into the pages of history. But it sounds like the U.S. is gearing up to send people back to the moon. Now, some people believe we might live in these balloon structures or tall soup cans. Most likely we'll have to live underground. But who would like to go to the moon as a future training mission to go to Mars? I know, if they would sign myself up, I'd go as well. Now, you're about to see this famous picture that's Buzz Aldrin inside that picture. I want you to picture you, yourself, as an explorer, as an astronaut. And does anybody know why all 12 men, so 12 men have walked on the moon, but no ladies. So ladies, I think it's time to go. Does anybody know why all of those footprints are living statues there on the moon? Yes, my dear. There's no wind. Oh, fantastic. I love this. So thank you guys for being smart explorers. So they're really, literally all like living statues there. So let's keep on traveling to our next location. And help me go. What's the next planet? Mars. All right, help me go. Keep on going there. Now, I have to tell you, Mars got so much more interesting. We were sending Opportunity and Spirit before that, Pathfinder and Viking. But it's like when Opportunity landed, when found these weird rocks they call blueberries. Now, you wouldn't want to eat one, it would hurt your tooth. But it's like it's got a lot of iron oxide hematite, which is basically rust. And to have any kind of rust, you would have had to have had water. So where did it go? How did Mars, if it was a planet full of water, where did its atmosphere go? What happened, right? And so now Curiosity has been sending us amazing pictures back. And then, did you guys follow this? I hope you did. In the spirit of exploration, we now have Opportunity and Spirit have gone to sleep, but Curiosity and Insight are there. If you ever look through a telescope when Mars is having a dust storm, and dust storms can last for weeks, it will look like the planet is actually changing color. It's home to the tallest volcano in all of our solar system, Olympus Mons, and it's about 3 times taller than Mount Everest. It also has a Grand Canyon, much like ours, Valles Marineris, about 4 times deeper, 10 times longer than our Grand Canyon. And a year, about 687 days. If you weigh 100 pounds on Earth, you only weigh about 38 pounds on Mars. But again, We saw Curiosity take amazingly cool vistas and pictures and send us back data. Now, its tires are beginning to wear a little bit out. But like I said, even InSight is there. I want you to think about InSight as a kind of doctor that has gone there to literally take Mars's temperature and get a feel for its heartbeat. I was talking to somebody and the kid goes, oh, they're gonna check for earthquakes. And I'm like, no, they're gonna check for Mars quakes. Can't check for earthquakes on another planetary body. So it will be fun to see as InSight drills down, listens to the very heartbeat of Mars, and see what we actually figure out even more about that red planet. Now, who would like to go and live on Mars someday? I know! I've decided if they would let grannies go, that one day they're like, my grandkids will be asked, what happened to your grandma? Oh, she went to Mars. So much better a way to go. Now, this is a little bit of a trick question, and this will get a prize. What is in between Mars and the next big planet? Do you know? The asteroid belt. There you go, full of cool, really cool stuff. All right, so help me travel to the asteroid belt here. Here we go. You gotta help me think again. Put those good brains to exploration, good use. Here we go. Now, most scientists believe the asteroid belt is simply remnants of when the solar system was forming. So they're just leftover bits and pieces, some tiny like a grain of sand, some huge. Ceres being the largest of asteroids, once upon a time considered a planet, now considered a dwarf planet. Vesta is probably considered the largest asteroid in the belt. And tonight we get to celebrate something else. OSIRIS-REx will slip into orbit around a near-Earth asteroid named Bennu. And here's what's exciting about its mission. In a couple of years, as it makes it's going to figure out a great location. It's going to go down and it's actually going to shoot the ground with some nitrogen. It's going to suck up all this primordially carbon-rich material. It's going to pack it away and it's going to send a return sample home. That's going to be amazing. That's going to give us more information about how did we form, how is it that we got to be, and how is it that we lived on such a grand Goldilocks planet like our Earth. So again, tonight as we celebrate New Horizons passing by Ultima Thule, let's also raise a glass to OSIRIS-REx that will slip into orbit around one of the most tiny of pathways there. And like I said, about 2021, it will return a great sample to Earth. Now, what is the big gas giant out there? Jupiter. Oh, I always like to make this thing. Does anybody know what kind of dinosaur that is? Right, that's what I think every time I hear OSIRIS-REx. All right, so let's get on to Jupiter. Help me think travel there. Come on. Oh, that is such good thought power you're doing there. It's so amazing. Good stuff. Awesome. Oh.
Jupiter has over 60 moons and takes 12 years to orbit the sun.
If you guys haven't been following the Juno mission, may I say what Dr. Scott Bolton and his team are doing is just remarkable. It literally, the images coming back look like a Van Gogh painting. We know that it is the big gas giant, and we know that it's 70% hydrogen and 30% helium, and that great red spot is a huge storm. But what Juno has figured out is that there are crimson-colored clouds that envelop that storm. It sees the kinds of winds that hopefully we'll never have to endure, from 300 to 400 miles per hour. But again, as you see these images, imagine a Van Gogh being inspired by all these. Home to the largest moons in all our solar system, Ganymede, of course, the largest moon in our solar system, and Jupiter's largest moon. All right, so what is that next place that we're going to get to go? Saturn, my favorite. Help me think travel to Saturn. Come on. Now we're about 848 million miles from our star, and that's how far Saturn is away. Oh, I love this planet. Yes. All right. And I hear it back there in the background someplace. And, all right, one of those things. Whoa, you guys are really speeding all that up again. Nice. Ah. Oh, geez. Oh, one of those times when we can launch rockets, but not this. Okay, one time. Let me make sure this is okay. You guys are super patient. Oh, that's Jupiter. Sorry, guys. What is going on? All right, well, let me just tell you about Saturn. So, its rings never, ever, ever, ever stop spinning. So, can I have some volunteers to come up here and help me? Yes, you. And let me see somebody back there, Bailey. All right, and you over here. Come on down. So, well, some of the things I love. So, I want you guys to pretend like you have invisible rings. Come on down. And I want you to pretend like you're hula hooping, all right? Just keep on hula hooping. Yep, so great. All right, because guess what? The rings of Saturn never, ever, ever, ever stop spinning. And that would get a little exhausting, but yeah. And so what Cassini found out that as it made all of its dives in between the rings, that it actually goes through in the innermost rings this process of ring rain, that all those dust and particles and ice and things are kind of raining down into the interior of the planet. And then they say that in the rings, some are tiny and some are huge, almost a half a mile across. Are you kidding me? So fantastic. So again, are anybody tired of being a Saturn ring yet? All right, keep on going, because here's the more amazing thing, and really one of my very, very favorite facts about Saturn is, guess what? If we could build a bathtub large enough, guess what? Saturn would float. What? It is less dense than, oh, keep on spinning. It's less dense than actual water. All right, so remember, the rings never stop spinning. There are many divides in between the ring systems, and guess what? It's less dense than water and could actually float. All right, let's give them all a big round of applause. And here you go. Oh, prizes to be given out. There you go. There you go. All right. Now, with any luck, this is going to be Uranus. Let's give it a try. All right, here we go, everybody. You guys are good at hanging in here and thinking amazing thoughts. No! What? You're giving me way too much power. All right, I know Uranus is back here. Let's just see. I'm going to try that again. All right, talk amongst yourself about this whole exploration thing. As you can, if you've heard the scientists say, it's no easy thing for this Ultima Thule tonight. The incredible distance that we're having to travel and the trajectory, and sometimes that even, yeah, there we go. Yes.
The giant blue-green planet has a family of 27 moons and 13 very faint rings, which are hard to see because they are dark in color.
Now, Uranus looks like it's been knocked over on its side. It's tilted at 99 degrees on its axis. Most planets look like little spinning tops as they go about the sun. Uranus kind of looks like it's breakdancing. Does anybody out there, can anybody break dance? You can break dance? All right, Bailey, you can break dance. You can lay on your side and do that thingy. All right, anybody else can break dance? All right, anybody want to give it a try? Come on down. Oh, yeah. Yeah, so down like that on the side. I'm not sure that's what it looks like, but I can only hope that that's what it looks like as Uranus goes about the sun. So, and it's like, you know what? We actually it could have been named George. You know, its benefactor, King George III, it's like Sir William Herschel really wanted to name it George's Star. And for reasons, well, Johann Bode came along and was like, no, Saturn is named after Jupiter's dad, so the planet after Saturn should be named for Saturn's dad. And Saturn's dad's name was Uranus. Doesn't get used much anymore. So, or we could have called it George's Star. So let's check out and see if we can't get to Neptune with some creative license here and make sure this is going to go well. All right, let's hopefully get to Neptune. We're getting about 2.6 billion miles out now. All right, don't lag. I'm going to need all that thought power. Make sure we get to the right spot. Ah, dang it. Somehow we skipped all over it. So let me tell you, you know what? It's kind of like, okay, Voyager 2 flew by it, and what we know about it is that it is a great big ball of gas, maybe even an ocean of methane down deep within, and so it's like Voyager 2 flew past it, but we still don't know a lot about it. It's named after the Roman god of the sea, but here's what we theorize, and this might be my favorite fact about the possibility on Pluto, on Neptune. And remember, it's like this is a theory, hasn't been proven, so it's only a hypothesis, but scientists theorize that it could actually rain diamonds on Neptune because of the way carbon forms. I don't know, but I would like to be the first Neptune diamond collector. Anybody with me? First Neptune diamond collector. All right, so let me go back one. I want us all to take a good long look here at Pluto. Pluto, I know many people, it's all like 3 billion miles from the sun. And it's got a little bit of a weird orbit, right? Everybody go, hi, Pluto. I love this guy. So, and I love this guy. It reminds me of It's a Wonderful Life, of like, take a good look at that face, right? Clyde Tombaugh's farm was heavily hit by a terrible storm. And because of that, it rendered him impossible to go to college and become an astronomer like he wanted. It did not deter him, however. So here's what happens. He builds his own telescope out of old farm machine parts and the headlights from his dad's old Buick. I think it's phenomenal. Here's the more phenomenal story. When he was in his 90s, the Smithsonian comes knocking and says, Mr. Tombaugh, is there any way that we could put that in the Smithsonian? And he thought about it for a minute and said, well, actually, I'm still using it. So can you imagine building something out of old farm machine parts? But what he did with that telescope is he started drawing pictures of what he was seeing in the sky, sent them off to Lowell Observatory. They were so impressed that Mr. Slifer hired him, and within about 10 months of the job, February 18th, Clyde Tombaugh discovered Pluto with a very painstaking process called a blink comparator. And he, to date, is the only discoverer and explorer that we know, discoverer of a planet whose ashes actually got to pass by the planet that he discovered. So that his ashes will also fly by Ultima Thule tonight. So again, let's give a big round of Clyde Tombaugh, one of the reasons that we are here tonight. So as important as he is to the story, so is this little girl as well. Her name is Venetia Burney Fair, and she was 11 years old. Her papa worked for the Royal Astronomical Society, and so they're discussing this newly discovered planet. She's like, Papa, I believe this newly discovered planet should be named after the god of the underworld because it's so far away and difficult to see. He goes off to his meeting. They can't decide. So finally he says, well, my granddaughter thinks it needs to be named Pluto. And that's how Pluto got its name. Pretty awesome, right? So, but after 76 years in our solar system, the same year in 2006 that New Horizons was launched, here comes the International Astronomical Union. Going, no, we need to decide what makes a planet a planet. I'm going to need 3 volunteers. I need a sun. I need a sun. Okay, you be the sun. Now, I'm going to need you are going to be my great Pluto. All right, you're the perfect size. Now I need someone very tall to be a very awesome celestial object. All right, you want to be tall? All right, you're tall. Come on over. You're going to be tall. So you're going to be a celestial object here in the path of Pluto. All right, so what is your name, sir? Trip. All right, you're this amazingly handsome celestial object, Trip. All right, you're going to be the sun. You're just shining out for everybody to see. Yep, awesome, good job. And what is your name? Ben. Ben. All right, so you're going to play the part of Pluto.
Well, my real name is Benjamin.
Oh, Benjamin. All right, which do you prefer? Benjamin. All right, we'll go by Benjamin. Benjamin Pluto tonight. May I touch your elbows? All right, I'm going to. So let's just think about it. They said a planet has to have 3 criteria. 1, a planet must be round. Well, is Pluto round? Yes. And then the second is like a planet must orbit the sun. Does Pluto orbit the sun? Yes. It just happens to trade places with Neptune every 43, 46 years. Who's counting? Here's where it falls apart. It says a planet must have enough mass to dominate the path in its orbit. So we're going to exhibit this. I'm going to grab you by the elbows here. Let's go. So here's little Pluto, just out here on the edge of our solar system, minding my own business, 3 billion miles out. And then, dum, 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 he encounters the very handsome celestial object over here. And little Pluto's like, it looks bigger than me, but I'm going to give it a try. Hi-ya! Hi-ya! I simply don't have enough mass to knock it out of the path of my orbit. But I think you got this. Come on, Benjamin, we can do this. Come on, together. Finally, Pluto can do nothing but the friendly thing. Give a little fist bump and go, my orbit's going to be just a little bit irregular. And so that's how, in a very rudimentary way, how it falls apart for dear Pluto. It simply doesn't have enough mass. But if you listen to Dr. Alan Stern, he says that anything 3 billion miles out there would have a little eccentric wobble and orbit. So we say a rose by any other name would still smell as sweet. A planet by any other name is still our planet. So let's give a big round for everybody who helped show us why Pluto's no longer a planet. All right, there you go. Oh, you already got one? All right, hold on, come on over. This one's super cool. All right, there you go. And there you go. And then there you go. All right, yay. All right. And thank you guys so much. So as we head out tonight, I know you guys want to go to dinner. We're heading deep into that epic outer edge of our solar system, into icy worlds, the ones we know about and the ones that we yet know of. And so tonight, as we celebrate this amazing, amazing feat of exploration, I will challenge you all to become explorers, to dream about where you want to go, to stand on the shoulders of all of these amazing science giants who are here and doing great and mighty things. And so it is the furthest object, beyond known worlds. That's what Ultima Thule actually means. So, as my last thing says here, Carl Sagan says that we are star stuff. From the very carbon in our DNA, to the calcium in our teeth, to the iron in our blood, we are made from the same elements as stars. You guys are the shining stars of the next generation of scientists, explorers, astronauts, and researchers of the future. Shine bright. Go do science. Make it awesome. Make our world and the future understanding of our world better. Let your mind revolve around this. The universe is always expanding. Let your mind do the same. And that's the view from Janet's planet. Thank you guys so much. Mwah.
And now let's check in on the progress of New Horizons using NASA's eyes on the solar system as the spacecraft approaches Ultima Thule. All right, well, we don't have the video this time, so what we're gonna do is we're gonna close out. This concludes the first part of the Ultima Thule flyby program. Thank you for joining us. We invite you to take a short dinner break and hope to see you back at 7:30 to start the countdown to Ultima. There's dinner, restaurants nearby. I've been told the Clobies, which is a barbecue place on the corner, actually has room and they're expecting a big crowd. That's an option, but feel free to do whatever you'd like for dining options. We'll start back at 7:30. We're gonna close the auditorium doors at 7:45 and the formal program will begin at 8 o'clock. Thank you, everyone.
We need solar flares. So please come up and see me so we can talk about that real quick. So please.